Good morning, everyone. I'll let everyone dial in before we start. So we'll give everyone a couple of minutes to join. Well, 30 seconds. All right. All right. So I'll slow down in joining. So we'll go ahead and start. My name is Ebony Roan. I'm your OpCert program coordinator, at least one of two at ADQ. Welcome. Thank you for attending. We're going to be covering chlorination and protecting water quality. Quite a few presentations for you today, so jump right into it. GoToWebinar guests, just so you know, professional development hours are available for today's webinar. The agenda is currently located in the handout section. If you look for a gray bar that says handout in your dashboard, you should see it. If you don't, just feel free to contact the OpCert program by email and we'll verify that you stayed and we'll send the agenda to you. The presentations will be sent out via share file. Webcams are disabled and all attendees are muted. So if you have any questions or comments, please put them in that question drop-down box. For future reference, this webinar is being recorded and will be uploaded to our YouTube channel within the next couple of weeks. If you're viewing as a group, please make sure all who are in attendance are registered to attend this webinar. We just want to make sure our records are good and straight. So if someone in the group needs to come back 3 years later and say, hey, I attended this webinar and I didn't get an agenda, we can at least verify on our end, because if we can't verify you attended, we will not send you an agenda. A little bit about our today's topics. Like I said, we're going to go into a bit of chlorination, chemical dosing and residuals. Move over to TTHMs and how acetate acids. And then we're going to get into a little bit of aesthetics, taste, odor, appearance. We're going to review our state rule for hauled water, and then we're going to end with some waterborne diseases and the distribution system. So we're covering a wide range of topics here. So just to start, we're going to go ahead and pull out a quick poll for everyone, just so we can gauge our audience. All right, so what is your role, your current role at your water wastewater system? This should be multiple choice, but if it's not, just the most prominent role you may have. And give everyone like 10 more seconds. Oh, until you tell this. All right, got a good amount here. All right, looks like most of you guys are operators, admin, foreman, supervisors. Thank you all for being here. So yes, this, in truth, yes, this webinar is geared towards you. So like I said, thank you very much. All right. What grade of certification do you currently hold? Like I said, this should be multiple choice. If not, just the the highest grade of certification you hold right now. All right. All right, we're going to close that. We got a lot of answers there. So most of you are grade 4, grade 1s, which does track. We saw a lot more foremen, more operators, responsible charges. Welcome. Just for our grade 4s, our webinars are geared more towards grade 1, grade 2, or entry level. But still, you should be able to find value out of this entire webinar for yourselves as well. And then last question. What brings you into today's webinar? We just want to get a gauge and see what kind of topics that we should be presenting more on, or if, like I said, chlorination has value added, is value added for your own professional development. And PDHs definitely I can count for continuous improvement, career development. All right, got a few here. All right, perfect. Go ahead and share that. So yeah, most of you are here for continuous improvement, professional development. We appreciate you staying. Like I said, the agenda is going to be in the handout section. All right. So moving on here, just a few reminders, certified operators, please make sure whenever you get your agenda, just go ahead and upload that as soon as convenience, at your earliest convenience. Always double check your portal regularly. Make sure you know your expiration dates that are coming up, and that you're actually within that period, not within the 90-day grace period, but within that 3-month period before your expiration date to renew. Just so you know, we did switch from Gov Delivery to Qualtrics. So if you're not currently receiving notifications for our operator certification events, workshops, webinars, please make sure you get onto Qualtrics to sign up for notifications. We're no longer sending notifications through Gov Delivery. And that's the QR code in case you want to scan it, or if you have a phone, you can scan that the URL code here, and that our phones are funny. You can take a picture of a URL and it'll just copy the text and take you straight to the site too. Just a few frequently asked questions here. Shorter certification periods with your newest cert. Some of you do opt in for common alignment and call, say, hey, why does my new cert only have 6 months, or why does it only have a year and some months? That's because you opted in for common alignment, which means your newest certification takes the existing certification's expiration date. We're no longer reversing this, so just a few reminders by the time you are ready to upgrade or renew. Deny the alignment if you plan to upgrade annually. Give yourself some time to take your exam. Make sure you can obtain the PDHs for your shorter certification period. We have an example there. The distribution one has a shorter certification period than the water treatment one. But to cover the renewal for the water treatment, you want to just make sure you have 30 PDHs for that distribution. PDHs only apply to existing certifications at that time. When in doubt, call the program, we'll help you out. And then, as always, our common alignment is not offered if the next expiration date is within 6 months. We don't want you to have to scramble for 30 PDHs in 6 months, pretty much. And then last one, a very, very, very quick demo. How do I upload my PDHs? Most of you are probably very much familiar with this screen. You're going to go ahead and press yes or no if you have a facility to add, and you want to be up here in this section, the Add PDHs section. You can search by description for your PDHs. If you already have it uploaded, you just want to make sure. You can edit any of these fields here and view it. But when you edit, that doesn't mean that the file changes. Once you upload a file, you no longer have access to it, but we do see it on our end. If you want to delete an entry altogether, you'll just press that delete button. And then if you ever looked at the top here and you saw this total, this isn't the total amount of PDHs you have. This is the total amount of entries you have in your portal. The number, the hours here, will only tally once you're prepared to renew. Okay, and with that, we'll go ahead, not yet, but we'll go ahead and we'll move on to our first presentation. Joe, are you ready?
Yes, can you hear me?
I can. Sending you the screen power right now.
Okay. Okay, can you see my screen?
Looks good.
Okay, good morning, everyone. No, it's early in the morning. Hope everybody's having their coffee. I am. My name is Joe Cornejo. I'm your presenter for this morning. Just giving you a little bit of background. I've worked a lot in water treatment. Currently 50 years old. I've been in the industry since I was 17. My last job working in water treatment directly at a treatment plant was for a company called EPCOR. And I was their manager for their central district potable water treatment. I worked at a really wonderfully designed plant called the White Tanks Water Treatment Plant. So if you look at the title of this presentation, it's Chlorination, Forms and Proper Use. I'm very familiar with chlorine in all its forms and its application when you're dealing with water treatment. So what are we going to learn? What's the objective of what we're going to learn in today's presentation? Well, what is chlorine? The history of its use. Now, this is very important for us to understand as treatment operators. List the different types of chlorine and their applications. It's also very important that we understand the concentrations and also some of the degradation shelf lives of these types of chlorines. And then we're going to explain how chlorine is used in drinking water. Simple thing. Now, the first question, that was a video. I'm going to skip the video because we're not going to have enough time to watch all the videos. But you're going to notice that we're going to detail enough information so that nothing really gets missed. So the question is, what is chlorine? Chlorine has been around for a while. Sometimes we think it's just something as of late, maybe early 19th or mid 19th century. It's actually discovered in 1774, and it's been in use since as a disinfectant. Originally, it wasn't a disinfectant, but then it became noted that it is a very effective disinfectant, and I'm going to get into what disinfection is in more detail in a later slide. But what is chlorination? Now, if you look at the slide as it reads here, chlorination is the application of chlorine to water for the purpose of disinfection. Now, this is very important for us to understand as water treatment operators, especially in this country. Chlorine is the most frequently used chemical for disinfection in the water treatment field. Is there other ways to disinfect water? Yes, there are. However, this is the most frequently used one and approved by the EPA. And why is that? Because you have other forms of disinfection, but because chlorine most notably leaves a residual. And it's very important for potable water to have a residual because it gives a very clear indication that the water is safe to drink. Now, getting back to the history of disinfection, you can see that since 1918, that's post-World War I, a lot of cities were already using chlorine for their disinfection purposes. So it's a very useful chemical, and it's vastly used today. What do we know about chlorine? What are some of the facts about chlorine? Well, one thing that we have to remember is that chlorine is corrosive. It is toxic. Now, if I were to ask you this question, what is the pH of chlorine? Well, it kind of varies, especially in liquid chlorine, but the pH will hover between 11 and 13 on the pH scale. Now, what does that mean? Well, it means that chlorine is very corrosive, okay? The weakest form of chlorine that we have most readily available is chlorine bleach that some of our wives go to Walmart and they purchase off the store shelf. That is about 3 to 5% chlorine, but that has a pH about 11. Now, many of you might think this is surprising, but if you put your hand in chlorine bleach and you maintain it for more than an hour, it will start to eat your skin away. So it is highly corrosive. It's not something that you want to touch for a long time. It's also, as you can see in the slide, it's a greenish yellow gas, and it's irritating to the eyes and the respiratory system. I mentioned World War I. Chlorine gas was used against the Allies in World War I. Chlorine gas, when it reacts with water, that means when it hydrolyzes with water, it becomes an acid. Our lungs are full of water. So when we breathe chlorine gas, we're basically acidifying our lungs. We can no longer breathe and we suffocate. Now, this is also very important to remember. Chlorine gas has a density of 2.5. That means it's 2.5 times heavier than air. There's a question that is sometimes asked on your level 1 treatment exam. It says, when you're designing a chlorine containment building, where are you going to place or where are you going to install the ventilation for that chlorine containment room? Because chlorine is 2.5 times heavy in air means it does not rise. It stays at the bottom. Do you see the picture here? That's a controlled experiment of a leaking chlorine gas container. You see what the gas is doing? It's staying near the ground because it is heavier than air. It does not rise. So what does that mean? That if I'm gonna install ventilation in a chlorine containment room or building, I better install that ventilation at room level. This is another very notable fact, is that chlorine will expand 460 times in air. What does that mean? Is that chlorine normally is contained in liquid form. You have 1 ton gas chlorine containers, you had 150-pound gas chlorine containers. You even have rail cars that are specifically designed to contain large volumes of chlorine, liquid chlorine. If 1 gallon of liquid chlorine escapes into the air, it's going to expand 450 to 460 times. Please remember that for your treatment exams. When you get asked, say you get asked the question, if 1 liter of liquid chlorine escapes into the atmosphere, how many liters of chlorine gas is it going to form? It's going to form 450 to 460 liters of air. And notice this next slide. It says here that chlorine is an oxidizer. What does that mean? If I was to ask everybody here, what is give me the easiest example of of an oxidizer. Give me an example of an oxidizer. Some of us go camping, right? When we're out camping out in the woods, we have a lot of fuel source out there. And what do I mean? We have a lot of firewood. And so we light a fire. Fire oxidizes. So in very simple terms, when you're chlorinating water, it's like if you're lighting it on fire. Sure, you don't see flames coming out of the water, but in very simple terms, chlorine is burning up materials in the water, namely organic materials and chloroorganics. And when it's doing that, it's going to remove tastes, odors, and colors of the water. Now notice it also prevents the growth of bacteria and slimes in our water. Sometimes in our distribution system, we're dealing with potable water, but we do get slime growth caused by and I'll make mention a little bit later in a later presentation, caused by iron bacteria. Well, proper doses of chlorine also help control those slimes and growths. Okay, chlorine sources. You got chlorine gas. Chlorine gas is 100% chlorine. You also have what's called sodium hypochlorite. I made mention of this a little earlier. Sodium hypochlorite is generally the type of chlorine that we use at our treatment plants to disinfect our effluent treatment stream to make it potable. That ranges from 12.5 to 15%. Although I will make mention that in the summer, there are some treatment plants that use 5% sodium hypochlorite. Why do they use it? Because it's a little bit more stable. It will survive the heat, so it doesn't degrade, and then the chlorine salts do not precipitate out of solution, rendering the chlorine less effective. So, but generally it's 12.5 to 15%. There are some sites around, EPCOR is one of them that I have experience with it, that have on-site chlorine production. So these on-site chlorinators, what they do is that they convert a sodium solution into 0.8% sodium hypochlorite, which is also very stable. A lot of these types of systems are not commonly used. They're very high maintenance and very expensive, sometimes to maintain the parts. But there is also on-site chlorine production, and the percentage of concentration of that chlorine, as you can see in the slide, is 0.8%. The last one that we're going to make mention is calcium hypochlorite. Calcium hypochlorite is those white hockey pucks. Those AccuTabs that we buy from Hills Brothers, those are 65% chlorine. So if I was to ask you, aside from chlorine gas, which is your most concentrated source of chlorine that you may have at your treatment plant, it's going to be those white hockey pucks. They are 65% chlorine. That's why you also have to be very careful when you're opening those AccuTab containers, because if a little bit of moisture gets in there, you're starting to release that chlorine gas. I mean, I'm one of those that will tell you that I've gassed myself several times in the course of my career opening an AccuTab container in which the integrity of the container was no longer good, and it leaked and it absorbed moisture. So when I popped the tab out of that container, all that gas came up and I breathed it in and it harmed my lungs. So you have to be very careful with that. Okay, so here we have an image of 150-pound chlorine gas containers. These are the white hockey pucks that I made mention, the calcium hypochlorite tablets. This here, sodium hypochlorite, is a 12.5 to 15% that we generally use to disinfect the water at our treatment plants. And then this is what our wives buy off the Walmart shelf, the Target shelf, or what have you. But this is chlorine bleach. This is the weakest form of chlorine that we have available to us, and that is 3 to 5%. Okay, so calcium hypochlorite is dry, comes in this form. Now notice what it says, that it degrades. So we're going to be keeping it in storage. You're losing about 3 to 5% of that chlorine strength per year. So you only want to have it in stock about 30 to 60 days. It does not do well with heat. So if you're going to store calcium hypochlorite tablets, do not, if at all possible, store them outside in the summer here in Phoenix, where you have 110 to 150 degree weather, because the heat is also going to degrade this material or this source of chlorine. Okay, and then like I said, it creates vapor pressure when it comes in contact with any moisture, and that's why when you pop the lid on that AccuTab container, you're gonna get gas chlorine escaping. And when you store these, make sure that you have a well-ventilated building so that the gases also are vented out. And when you walk into that building containing those AccuTap containers, you do not breathe in that leached out chlorine gas. Let's talk about a little bit about chlorine gas. Chlorine gas is the cheapest form of chlorine to use. It's also the most effective, but it's also very dangerous. We mentioned in a previous slide that chlorine gas expands 450 to 460 times when it escapes out into the atmosphere. That's why if you're applying chlorine gas, you do not want to have a chlorine application room anywhere near a school, anywhere near a neighborhood, a mall, a hospital, anywhere where people can be affected should that chlorine escape. It is a compressed liquid. Now, if you see what the slide says right here, it comes in 150-pound cylinders, it comes in 1-ton containers, or it even comes in rail cars. Now that gas is compressed into a liquid form into those cylinders. That's why you have to be, it's extremely important that we use a lot of care in how we handle these cylinders so that we don't expose ourselves or expose anybody else to chlorine gas. Okay, this is a 150-pound chlorine cylinder. This is what they look like. They don't weigh 150 pounds. They actually weigh over 300 pounds, but the liquid chlorine that they have inside of them is approximately 150 pounds liquid weight. Now, just as a general rule of thumb, I saw that when we did the survey at the beginning of this presentation, that a lot of you, some of you are taking your treatment exam. So I'm going to ask you the question, in one day, how much chlorine gas can I allow to inject out of that 150-pound chlorine cylinder? I'm going to repeat the question. How many pounds of chlorine gas can I allow to lead or to inject out of that chlorine cylinder in one day? The answer is 40 pounds. For a 150-pound chlorine cylinder, only 40 pounds of chlorine gas can be allowed to inject out of that chlorine cylinder in a day. And what happens if I go over that? You're going to ice up the cylinder, and if the cylinder gets iced up, you can no longer inject gas out of it. This is what a 1-ton chlorine container looks like. Once again, it weighs more than 1 ton. It's actually the liquid chlorine inside the container that weighs a ton, or approximately a ton. Now, the same thing, I'm going to ask the same general question. This may come out in your treatment exam. How many pounds of chlorine gas am I allowed to inject out of a 1-ton chlorine container in a day so that I don't ice up the container?
Hey, Joe.
Yes.
We got an answer. Is 3,700 pounds the answer?
No.
Almost.
Out of a 1-ton chlorine container, it's 400 pounds.
Close.
So 400 pounds, remember that for your treatment exams. And this is a chlorine rail car. Yeah, that's what they look like. Now, normally you wouldn't expect them to have that type of graffiti, but they're large containers. I don't really know off the top of my head how many pounds of chlorine, liquid chlorine they actually contain, but you can imagine that they contain a lot. And if anything is going to leak out of any one of these cylinders, this is the one that you want to really avoid any types of leaks from. Okay, time is pushing me, so I got to continue on. But this is a graphic of a chlorine injection diaphragm that goes over a 150-pound chlorine cylinder. And the way they basically work is that these cylinders, you just crack the opening valve or the outlet valve, the cylinder valve, just half open. And then the chlorine gas is going to go through a flow meter, after which it's going to go through an injector that's connected to a pipe. The injector has like a Venturi type device that's going to suck in the gas as the water flows by the injector. I don't know if you can see my mouse here, but this is where the gas is going to be sucked into the treatment stream so that you disinfect your water. Okay. These are just, this is what a tablet chlorinator looks like. And you insert the tablets in these cylinders. There's different forms depending on the manufacturer. But as water goes in this inlet and exits, it's basically dissolving the chlorine tabs, and that's what's distributing the chlorine through your treatment stream. And like I said, there's different types of chlorine cylinder injectors based on the manufacturer. Okay, now getting into sodium hypochlorite. Sodium hypochlorite, we're very interested in this one because this is the one that we mainly use at our treatment plants, at least here in the state of Arizona. It is just like the chlorine, the liquid chlorine glass. It's yellowish green in color. Now it's 12 to 15% strength, except for that 5% exception that I made mention of earlier. It's relatively stable if you maintain the right environmental conditions for it. Now look what it says right here. It says that heat very rapidly degrades sodium hypochlorite. So in the summer, you want to be going through your chlorine really quickly, or you don't want to be purchasing as much and filling up your tanks so that your storage time is no more than 30 days, because after 30 days, you're going to be degrading that liquid chlorine, and it's not going to be as effective to disinfect your water. Okay, this is a hypochlorinator type of skid. You have your hypochlorite in a tank. You're going to have your injection pumps, and your injection pumps inject the chlorine straight into your treatment stream. I'm just going to make mention of what chlorine dioxide is, because it's also a form of chlorine. There is just one city here in the valley that I know uses chlorine dioxide, but the majority of us don't. But just something to remember, chlorine dioxide is chlorine, but it's a stronger form of chlorine. Now, I need you to please keep this in mind. Chlorine dioxide is considered potentially toxic at a concentration greater than 0.8 milligrams per liter. You're going to see why we're making mention of this, because we're normally accustomed to seeing that the maximum milligram per liter or part per million dose that you can have in your treatment stream is 4.0. It does not apply to chlorine dioxide. Chlorine dioxide is way more powerful than just general chlorine. So the concentration should be no more than 0.8. And that's another thing that may be asked in your operator exams. So the reason that we use chlorine is that we have to disinfect water. Now I ask the question, is disinfection the same thing as sterilization? No, it is not. As you can see in the slide, the process of disinfection is that you're inactivated pathogenic organisms. You're not necessarily destroying them. Does chlorine kill pathogens? Does it kill bacteria in the water? Yes. Does it kill all the bacteria in polymer? Probably not. It just inactivates them. What does that mean? It means that it basically does not allow for this bacteria to reproduce. Maybe some of you are listening to this webinar, and as you're listening to this webinar, you're hearing me talk, you have a bottle of water, and you're drinking from that water this morning. That bottle from which you're drinking out, that you probably went to Costco and you bought a case of it, that can, for purposes of argument, that can have a pathogen in it. But if that water has been disinfected, you're going to drink that pathogen and nothing is going to happen to you. Why? Because that pathogen can no longer reproduce once it enters your organism. When we drink something, especially something that contains bacteria or a pathogen, our bodies are an ideal environment for them to just explode in population. And so that's what happens when we drink water that's not disinfected. We drink it, and whatever pathogen enters our organism starts to reproduce so fast that our army of defense, which is our white blood cells, get overwhelmed by this army of pathogens. And that's when it starts doing harm to our organism. But when water has been disinfected by chlorine, that pathogen, if it's still alive in that bottle of water, can no longer reproduce. You drink it, it cannot reproduce inside of your organism. And here come your white blood cells. They surround him and take him out. That is the difference between disinfection and what is called sterilization. Sterilization is a complete destruction of all living organisms in water. Now the question is here, how do you sterilize water? Well, you heat it up to 212 degrees Fahrenheit. That is to say, you boil water. Now, quick question. If you had to issue a boil order notice in your distribution system, for how long should you boil water? This is just to get you to think. You need to boil water for at least a minute for that water to be considered safe to drink. Why don't we boil water before we send it on to distribution system? Because it's a lot cheaper to use chlorine and disinfect that water. And that's why we use this primary disinfectant. Okay, moving right along. So chlorine keeps the water safe. It keeps it safe from different types of waterborne diseases. That we're going to talk about a little bit later in another presentation that I'm going to be giving. But look what it says right here. This is all about chlorine contact time. Chlorine needs to have a certain amount of contact time in the water before it inactivates microorganisms. Just as a general rule of thumb, remember this: the higher the chlorine dose, the lower the contact time. The lower the chlorine dose, the longer the contact time, and that's just common sense. And as a general rule of thumb, this is just something that we know as operators. Chlorine needs at least 15 minutes of contact time to inactivate microorganisms. Of course, that is going to vary according to circumstances. But generally, the contact time should be 15 minutes. Recommended contact time should be 30 to 45 minutes. It's interesting, this fact right here, that there's a pathogen in water, an organism called Cryptosporidium. That one needs 10 days of chlorine exposure, 10 days of contact time for it to be destroyed. And that's why there's other forms of disinfection that are more effective than chlorine for taking out that type of contaminant. Okay. When we chlorinate water, we want to inactivate pathogens. So you see right here, this is a regulatory requirement of inactivation. As a general term, we have to achieve a 3-log inactivation of Giardia. 3 log means, look, 3 digits from the decimal point, 3 log. This is 4 log. Viruses must have a 4-log inactivation. How do I guarantee that activation? You make sure that you have the proper contact time. Okay, just a little bit of chlorine terminology. You got chlorine dose, that's what you add initially to the water. You got chlorine demand, that's how much is used up in the water, and then you have chlorine residual. Okay, what is the minimum chlorine that you should have in your distribution systems at all times? As you look at this slide, it should be no less than 0.2 milligrams per liter. That is where you're expected to maintain in your distribution systems at all times to make sure that your water is properly disinfected. What is the highest amount of chlorine that you should have in your potable water? If you look right here, it's 4.0 milligrams per liter. Now remember, chlorine dioxide, these parameters do not apply. The limit of chlorine dioxide, the minimum is 0.1, but the maximum is 0.8. So do not let that confuse you when you're taking your treatment exams. Chlorine dioxide, the maximum contaminant level is not 4.0, it's actually 0.8. Okay, let's get in a little bit into chlorine chemistry. Chlorine, when it reacts with water, it hydrolyzes with water, especially chlorine gas, it forms 2 compounds. One of them is called hypochlorous acid and the other one's called hydrochloric acid. But just as a general rule, I want you to remember that chlorine has a pH of 11 to 13. That is not acidic. That is considered basic. But when it reacts with water, it becomes an acid. Anything acidic on the pH scale is considered anything below a pH of 7. So if I'm going to ask you, I'm just going to appeal to your common sense. I'm going to ask you, if I'm chlorinating water, at what pH do I have the best disinfection if I'm using chlorine? Anything below 7, because chlorine becomes an acid in water. So once you get any pH above 7, you're not chlorinating as effectively. Now look right here. When I chlorinate water, I'm going to form 2 compounds. One of them is called hypochlorous acid, and the other one is called hypochlorite ion. I like to use this slide. Hypochlorous acid, hypochlorite ion. This is Dumb and Dumber. That's Harry and Lloyd. Why am I using this slide? Because hypochlorous acid, we'll call it Huckle, is stronger than alkyl. You ever seen that movie? Lloyd used to beat up on Harry all the time. Hypochlorous acid is 80 times stronger than hypochlorite ion, especially if you're going to be destroying pathogens. Now you're probably asking me, well, Joe, how do I know if I have more hypochlorous acid or more hypochlorite ion? Remember, chlorine becomes an acid in water. If you have a pH of 7 or below, you're going to have a higher concentration of hypochlorous acid. If you have a pH of 7 or above, a lot of your facilities have well water that has a pH of 8, you're going to have more hypochlorite ion in your water. Are you still disinfecting the water? Sure you are, but not as effectively as if your pH was lower. So we know as a fact that the pH level affects chlorination. I'm just going to have to breeze to some of these slides. These are going to be made available to you later, so you can make reference to them. I'm going to briefly talk about what's called breakpoint chlorination. It's very important as operators that we understand what breakpoint is. Breakpoint is when you're adding chlorine to water in whatever its forms. But that chlorine is going to destroy or react with all the organics and all the ammonia in the water before it becomes what's called free chlorine. Okay? As distribution system operators dealing with potable water, we're very interested in free chlorine. Free chlorine is composed of hypochlorous acid and hypochlorite ion. You do not get free chlorine until you destroy all the organic compounds in the water and all the ammonia in the water. Once that reaction occurs, you hit what's called breakpoint. As soon as you hit breakpoint, the species of chlorine that you're going to have in your potable water is going to be free chlorine, not combined chlorine. So this asks a question here: are public water systems that put out potable drinking water, are they chlorinated past the breakpoint? Most definitely, yes, they are. And the chlorine levels that we have to maintain in our water have to be no less than 0.2 and no greater than 4.0 parts per million. This is just a side reminding us of that. Chlorine should be no more than 4. Chlorine dioxide, no more than 0.8. So we kind of went briefly that pH affects chlorination. There's another thing that affects chlorination, and it's called turbidity. Turbidity affects chlorination greatly. What is the turbidity of drinking water according to the EPA? What is the regulated amount that should be going in our distribution systems? The regulated amount is 1.0 NTU. Now that's another abbreviation that we're throwing out at you this morning. NTU means nephelometric turbidity units, and it's a measure of the clarity of the water. Now look at this slide right here. When water has no turbidity, the chlorine molecules go in, and these little dots representing the microbes are directly attacked by the chlorine molecules. But when water has turbidity, especially a turbidity of greater than 1.0, you have these particulates in the water. They could be organic particulates. The bacteria will hide in these particulates so that the chlorine molecules cannot reach them. So does the turbidity affect chlorination? It most definitely does. It's very difficult to chlorinate highly turbid water. Okay, I think I've gone over my time limit. I'm sorry that I went over 3 minutes, Ebony. This is a topic that I really enjoy, and there's so much information that can be taken out of it.
No, you're good. You're good. If anyone has any questions just covering chlorination in general, please drop those in the chat. But right now, I think we're good. We did see someone mentioned. Oh, okay. That is a different question, Jim. We're pretty much covering here. Let's see. One second. Go ahead and continue, Joe.
Okay.
We'll answer that question at the end, Jim, of this presentation.
Yeah, I'm just going to go into the next. Okay, very good. Now this next presentation has to do with chemical dosing of residual. What kind of chemical dosing? This is a chlorination workshop, distribution workshop. The chemical that we're most interested when we're disinfecting our water is going to be chlorine. So we have to properly know how to dose chlorine. Now, these are very important questions for us to add, because I'm just going to create a very hypothetical scenario of something that occurred to me when I was working for a water treatment company. I had a 3 million gallon tank. It contained 3 million gallons of potable water that was going to feed a distribution system. 1 week, we had a positive coliform hit from the water coming out of this treatment tank. So we went to troubleshoot the system of why we got that positive coliform hit. We found out that our hypochlorinator, our liquid chlorine injection, was not working. So we had to chlorinate that tank. We had to get that tank immediately chlorinated. So my boss, my director says, Joe, immediately chlorinate that tank to 1.5 milligrams per liter. Now, mind you, this tank has 3 million gallons of chlorine in it. And I had a 55-gallon drum of 12.5% sodium hypochlorite at the facility. And so I told the supervisor, who was my direct responsible charge, I need you to take that 55 gallons and I need you to determine how many gallons of 12.5% sodium hypochlorite you need to chlorinate that 3 million gallon tank to produce a 1.5 milligram per liter dose. And believe it, there's not a lot of operators that know how to do that. The supervisor in question, when I asked him to do that, he just gave me a blank stare. He goes, well, do I put the whole drum in? I go, no, you're not going to put the whole drum in. You're going to overdose it. I said, let's go over the calculation of how you actually do that. Some that we as operators, it's very important that we need to know how to properly dose chemicals and calculate calculations. And that's what this presentation is all about. Okay. We're going to get into the basics of chlorine dose, demand, and residual, especially for that 5% at the beginning that says that they're attending this seminar for reasons of their certification. This is some important terminology that we need to know. Look at this definition. This one is talking about chemical. Look where my mouse is, dosage. What is dosage? Dosage is the amount of chlorine applied in pounds per day, milligrams per liter, or parts per million. Any one of these parameters can determine your dose. What is the demand? Demand is the amount of chlorine used up by chlorine reducing agents. I touched on it, albeit briefly, in the previous presentation. Organic materials in the water is a chlorine reducing agent. Ammonia in the water is a chlorine reducing agent. Until the chlorine neutralizes all the ammonia and destroys all the organics, you're going to have a chlorine demand. Once that demand is met, if you've dosed enough to cover the demand, you're going to have what's called a chlorine residual. How does it define chlorine residual? Is the amount of chlorine left after the demand has been met. Now, I made mention, why do we here in the United States, why do we use chlorine? We use chlorine because it leaves a residual. You add a reagent to that water, and when that water normally turns pink, it's letting me know that there's still chlorine in the water. That means that that chlorine had nothing left to react with. The demand was met. This is just an example of a colorimeter. This is a chlorine tester. This is a Hawk DR300. Now you see right there on the screen readout, it says that I have a chlorine residual of 0.91 milligrams per liter. When I added my DPD reagent, it turned pink like that. That means that I had a residual. What does that mean? It means that that I dosed it enough so that the demand was met and there was still leftover chlorine. What does that pink tell the regulators? It tells the regulators that that water that we're sending out into our distribution systems is safe for our customers to drink. This is the basic principle of chlorine dose, demand, and residual. The dose minus the demand is going to equal the residual. The demand plus the residual is going to equal the dose, and the dose minus the residual is going to equal the demand. If you're hearing this for the first time, it may seem a little confusing. And I do know this for a fact that the majority of operators fail these questions the first time they take it, but it's not really that difficult to understand. Let's just say that for argument's purposes, I'm going to hold my mouse over dose right here. Now I need you to use your imaginations for this. Imagine that the dose that I'm applying to my water is 3 parts per million. That's how much I'm dosing the water in. I have a certain quantity of particulates, organic particulates in the water, so that the demand of that water is going to be 2 parts per million. So I started off with a dose of 3, the demand was 2, I'm going to have a residual of 1. It's very easy, very basic to understand that. Okay, if I have a demand, if I have a known demand of 3, and I have a residual of 1, it lets me know that my initial dose was 4. Because 3 was used up by the water, 1 is still left over, so my dose was 4. If I'm trying to figure out the demand and I know what the dose and the residual is, let's just say that I knew that I put in or that I injected 3 parts per million of chlorine into my water, and I have a 1 residual, then what was the demand? What was the dose minus the residual? The dose minus the residual means that my demand is 2. Let's practice that in these next set of questions right here. So what is the chlorine dose in milligrams per liter from a chlorinator if the chlorine demand is 1.12 milligrams per liter and a chlorine residual of 0.2 milligrams per liter is maintained throughout the system? That sounds a little more complicated than what I explained in my previous slide. Now, why? Because now we're dealing with decimal numbers. And now we're reading a question. And that's what a lot of operators, we need to get used to at reading questions like these and be able to understand what we're reading to be able to come up with a solution. So here it's telling me that demand is 1.12 and that my residual is 0.24. Now, if we go back to this slide, then we can use the dose minus the demand to determine the residual. Now look how this is broken down. It says add the known chlorine demand to the known residual to get the initial dose. So the demand was 1.12 and I have 0.24. That means that I must have dosed 1.36 milligrams per liter to my water. Okay, let's practice another one. This is question number 2. Estimate the chlorine demand for water in milligrams per liter if the chlorine dose is 3.63 milligrams per liter and the chlorine residual is 0.2 milligrams per liter. So once again, now here it's telling me how much I actually put in and how much I have left over. What it's not giving me is demand, so I have to figure out the demand. How do we do that? Well, to get the chlorine demand, subtract the initial dose from the known residual. The initial dose was 3.63. That's how much I actually injected into the water. I have a residual of 0.42. That means that there was enough organics and enough maybe ammonia in the water that it chewed up 3.21 milligrams per liter of chlorine. That was my demand. Right. This one has similar numbers, but it's not the same question. You're probably going to think, Joe, this is the same question. No, it's not. Estimate the chlorine residual for water in milligrams per liter if the chlorine dose is 3.63 and the chlorine demand is 0.42. Same numbers, but we're going to have a different result. But to get that, what we need to do is that we need to subtract the dose from the residual, and then that was how we get the demand, which is 3.2. Okay, just a little reminder, we're going to talk about breakpoint chlorination. Remember that breakpoint chlorination is when you destroy all the organics in the water and then there's no more ammonia in the water. You see how it says right here, formation of chloramines, destruction of chloramines. When you have a chloramine in water, that's what's called combined chlorine residual. It's chlorine combined with ammonia that forms a chloramine. One of the best examples that I use is that when you go to the hotel pool and the hotel pool smells of a strong chlorine odor, does that mean that there's too much chlorine in the water? No, it actually means the opposite. It means that there's not enough chlorine in the water. You actually have chlorine and ammonia bound together, and that's what's putting off that off-putting chlorine odor. And what do you need to do? You need to up your chlorine dose so that you destroy the ammonia. Where does the ammonia come in pool water? It comes from urine, or it comes from the sweat off our bodies. Maybe somebody was working out at the hotel gym and he decides to take a dip in the pool. All that ammonia from his sweat is going to go into the water. It's going to combine with the chlorine and it's going to form a chloramine. When we're dealing with potable water, we do not want chloramines in our potable water systems. We want free chlorine residual. You do not have free chlorine residual until you hit breakpoint. So it's very important that we know how to dose enough initial chlorine to destroy whatever chlorine reducers are in the water to get free chlorine residual. Now, what is free chlorine residual? Remember, it was HOCl and it was OCl. It was hypochlorous acid and hypochlorite ions. The levels of chlorine, once again, if you're at 0.2 or below, you are in violation of not meeting your chlorine residual. If you're above 4, you are also exceeding your chlorine residual. Now, a quick question for everybody here. What is the ideal, what is the recommended chlorine residual that you should have in your water? This is something that's actually on your treatment exam. If you would have asked me that question maybe a couple of years back, I would have said it was 1.0 because that's what I like to keep mine. mine distribution systems. But actually the recommended residual is 0.5. 0.5 milligrams per liter is a recommended chlorine residual that you should have in your water. Okay, now let's get into a little bit of meat of our presentation. This here that you see here is called the Pounds formula. This is called the Davidson's pie because Davidson is the engineer who invented it. It's a really ingenious pie. It's not a tasty one. You can't eat it, but it's kind of magical because what this Pounds formula does is that if you have, and I made mention that earlier, I used an example of a 3 million gallon storage tank, and I needed to dose that tank at 1.5 milligrams per liter of chlorine. What does the Pounds formula do for me? It's as if I evaporated all the water out of that 3 million gallon tank and I just left dry chlorine at the bottom. That's what it does for you. It takes all the water, it evaporates it out, and it lets you know how many pounds of dry chlorine you actually have in any given volume. That's what this pie does for you. Now, if you look at this pie here, I just need you to understand something, is that this symbol right here, you see this line that I'm drawing with my mouse? That symbol in mathematics equates to a division symbol. So if I have a dividend up top and a divisor at the bottom, this here is a symbol for division. Okay, so what that basically means is that pounds is at the top. Pounds can be divided from the bottom three factors to find a missing factor. Now I'm going to explain that. I've got million gallons per day here in one partition. I got 8.34 pounds per gallon in another partition, and milligrams per liter in the third partition. What that basically means is that million gallon per day volume times 8.34 times milligrams per liter. If I multiply the bottom three factors together, I get pounds up top. Or there's sometimes that I have the final pounds, but I'm missing a factor back here. So maybe I know that I injected 50 pounds in 3 million gallons and that a gallon of water weighs 8.34 pounds, but I don't know the milligrams per liter. So what I do is, once again, this is a division symbol. Now I divide to find the missing factor. I divide the 50 pounds by 3 million gallons, and then by 8.34, it's going to give me the missing factor. The same thing would happen conversely. If I know that I have 50 pounds of dry chlorine in my 3 million gallon tank, what I do is, and I know I dosed at 1.5, so I take the 50 pounds divided by 1.5, then divided by 8.34, and lo and behold, I'm going to get 3 million gallons. Okay, we're going to practice that in a further slide, but I hope that information makes sense. Now look at this slide right here, because this is very important for us to understand as well. Some of us sometimes have to swab pipes out in our distribution systems. We have to sometimes disinfect storage tanks. So how do you dilute one concentration to another concentration? Now, I like this slide example here because I have two beakers here. Now, if you notice here, these purple balls here represent, let's just say that's chlorine molecules, okay? So this beaker here has a certain volume of water, and I would say this is about maybe 1/6 full, and it has 6 chlorine molecules. This water here, being that it has less volume of water, is more concentrated than this volume here. Now you notice that this beaker now is half full of water, but it still has the same amount of chlorine molecules. So if I was going to ask you, how do you dilute one concentration to another concentration to get a desired solution? Well, look at this problem here. Look how it is asked. It says if 10 gallons of a 5.25 hypochlorite solution is added to a 55-gallon drum, how much water should be added to the drum to produce a 1.8% hypochlorite solution? So, okay, so let's just pretend that I'm your boss. And I just say, hey, look, you know what? I don't want you injecting 5.25% hypochlorite. I need you to inject 1.8. So I need you to take that 10 gallon, it has 5.25% hypochlorite, add it to that hypochlorinating drum, which is a 55-gallon drum, but I need you to dilute it down to 1.8%. Add the necessary amount of gallons to dilute that down. How do I do that? You know, this is basic high school algebra. Whenever I'm teaching a math class, I always like to ask the class, something that my freshman algebra teacher used to ask us every time that we used to show up to class in the morning. She used to say, "Good morning, class," and we'd say, "Good morning, teacher." She says, "Class, how do you solve for x?" And we used to always answer, "You isolate x." Every single morning she would ask us that. And it would drive us nuts, but you know what? It worked, because here I am more than 30 years later, and I remember that. How do you solve for x? You isolate x. When it comes to mathematics, what does x represent? X represents what you don't know, the unknown. Remember that program that used to come out on TV, the X-Files? The unknown files had to do with aliens and werewolves and monsters. Ooh, the unknown. Well, X in mathematics means the unknown, what you don't know. So we're reading this problem. What don't we know? We don't know how many gallons we need to add to dilute that 5.25% to 1.8. So X is the unknown amount of gallons. So how do we solve that? Well, once again, here, now I'm the teacher and you're the class. Class, how do you solve for X? And I hope that you're saying back, you isolate X. Look how we do this. Now I just have an asterisk up here. It says this volume began with 10 gallons, such that 10 gallons would need to be subtracted from the final result. So this is a proportion. 10 gallons of 5.25% is going to equal X gallons of 1.8%. So 10 times 5.25 is going to give me 52.5, and that's going to equal 1.8x, because X is the unknown. We do not know how many gallons we need to add. Class, how do you solve for X? You isolate X. And how are we going to isolate X in this case? We're going to isolate X by dividing both sides by 1.8. You see, this side of the equal sign gets divided by 1.8. This side of the equal sign gets divided by 1.8. Oh, sorry. When I do that, X gets isolated, and when I divide 52.5 by 1.8, I get 29.2 gallons. So the X is no longer unknown. So I need to have 1.8% divided in 29 gallons. But remember, I began already with 10 gallons. So I have to subtract the 29.2 gallons minus the 10 initial gallons. That means that you need to add 19.2 gallons to dilute that chlorine solution down to 1.8%. So just please remember that. How do you solve for X? You isolate X. Okay. Let's put the pounds formula in its correct application. So remember, the pounds per day is going to equal the dose in milligrams per liter times 8.34. Now this right here is going to be my unknown. And my unknown so far is going to be my million gallon volume. So look at this next question here. Determine the chlorinator setting in pounds per 24-hour period to teach a flow of 3.4 million gallons per day with a chlorine dose of 3.35 milligrams per liter. What is it asking me for? It's asking me to determine how many dry pounds I need. So if I go back to the pounds formula, this is my unknown, the pounds up top. So I have to have these three bottom factors to be able to calculate for the top unknown. And do I have them? I believe I do. I have 3.4 million gallon per day volume. I have a concentration of 3.35, and I know for a fact that a gallon of water weighs 8.34 pounds. So look what's going to happen. I know my flow, I know my concentration, and I know 8.34. So when I multiply the bottom three factors, I'm going to get the top factor in pounds, which is 95 pounds per day. So my chlorine setting better be at 95 pounds per day on my chlorinator. Okay, let's go. Let's try another one. Question number 2. A chlorinator feeds 51.33 pounds of chlorine per day to a flow of 0.831 million gallons per day. What is the chlorine dose in milligrams per liter? So once again, here, which one of these is my unknown? I do not know concentration. I know pounds. See, the 51.33 is going to go up here up top. I know that a gallon of water weighs 8.34. That's just a given. And I know that I have a volume of 0.831 million gallons per day, and that's going to go here. What I don't know is a concentration. So remember that this line right here is a division symbol. So whenever I have two of the bottom factors that I know, I could solve for the missing X factor by dividing the top. So pounds, which is 51.33, is going to be divided by 8.31. and then it's going to be divided by 8.34, and that's going to give me the dose. Look how it reads. Okay, 51.31 pounds divided by 8.34 divided by 0.831, and look what my dose is, 7.4. Okay, time is pushing us, so we have to keep moving.
About one more slide, Joe, we got time for.
Okay. Okay, this one asks, how many pounds of chlorine are there in 165 gallons of 2.5 chlorine solution? So how do we solve this? This is very basic. 165 divided by a million turns it into million gallon decimal form. Okay, so then we plug all those known factors into the pounds formula. Now right here it says 2.5. Now one thing to remember is that 1% when we're dealing with concentrations is equivalent to 10,000 milligrams per liter. So now I have all the factors that I need. I have my concentration is 25,000 milligrams per liter because 2.5 times 10,000 is 25,000 times 8.34 times my volume, but in million gallon decimal form, which is 165 divided by a million. So I multiply these three factors together and I get 34.4 pounds of chlorine. Okay, sorry that it went a little over, Ebony.
That's okay. We can wrap up, or we'll definitely get all of these presentation slides to you guys through a share file at the end.
And if you notice, I'm going to interject, Emily. The last question that I can break down, it's got a really nice breakdown of how it's explained. And it basically tackles how many gallons of a certain percent solution do you need to add to a volume to get the desired concentration. So when the guys look at this breakdown, they're going to be able to solve that problem.
Perfect. Well, thank you very much, Joe. If you have any questions, feel free to put them in the chat. We'll have Joe back again by the end of the webinar, and he can follow up with you there too. Thank you again, Joe.
You're welcome.
All right, perfect. Let's go ahead and move on to our next topic. We're talking about triomethanes and haloacetic acids to highly regulated disinfection byproducts. Allison, are you ready?
Yes, I'm ready.
All right, screen power is yours.
All right. Okay. Is that looking good to everybody?
You can see your screen, yes.
Okay. Get that out of the way. So, okay. All right. So I think everybody's ready. I'll go ahead and get going. As Ebony said, I am presenting total trihalomethanes and haloacetic acids. These are disinfection byproducts in drinking water treatment. My name is Allison Shepard, and I'm with the City of Phoenix. So a little bit about me.
Excuse me, Allison. Sorry to interject. We don't see your full presentation. We just see your slides.
Oh, no. Okay, hold on. No. No. Okay. Does that work?
That's better. There you go.
Okay. All right. Sorry about that. Here we go. All right. So a little bit about me. My first time using GoToWebinar, so there's that. Again, my name is Allison Shepard. I'm a Chemist 3, City of Phoenix Water Services, and I have 25 years experience in the water industry. I got my Bachelor of Science in Chemistry from the University of Arizona, Bear Down. I've worked in the Phoenix Water Labs for about 13 years before moving on to supervising for the last 12. So I currently supervise 14 analysts at 5 water and wastewater treatment plants, and they perform 500 process control tests daily. I also have my grade 4 ADQ certifications in both water treatment and wastewater treatment. All right, so disclaimer, I know we have operators viewing today from all kinds of different systems, small systems, large systems. I just want to say disclaimer is that my experience is completely with a very large surface water system. So just to give you an idea, Here is a picture of our distribution system. This is actually something that we use to kind of keep an idea of where all of our THM sampling sites are, as well as our storage tanks. So we provide water to the 5th largest city in the US. We have an area of approximately 540 square miles and a population of approximately 1.66 million people. We have about 1,500 employees, 5 water treatment plants that we're operating currently, and 7,000 miles of water main. So that's a big system. So we've got our surface water from the Salt and Verde rivers that we treat at the Val Vista, Deer Valley, and 24th Street water treatment plants. And those produce about 50% of our water. The Colorado River water is treated at Union Hills and Lake Pleasant water treatment plants, which produce about 47% of the city's water. And then groundwater wells are used for the remaining 3% of water used in the city. So as you can see here, a lot more surface water than groundwater. I will try to mention groundwater when I'm able to, just to kind of give examples and stuff like that. All right, so this presentation is going to talk a little bit about disinfection and disinfection byproducts. I just want to thank Joe for going over disinfection there. That was really good, just to give us the background of what we're talking about today. So I'm going to talk a little bit more in depth about the byproducts that occur when you're disinfecting. So going to go over the background of Safe Drinking Water Act and the disinfectant and disinfection byproducts rules, as well as do a really quick overview of disinfection, disinfection byproducts as a whole, and then talk more in depth about THM, total trihalomethane, and haloacetic acids, reduction and control, monitoring, reporting, and challenges. So just to go into this background, so the Safe Drinking Water Act was originally passed in 1974. This picture that we are showing here is a woman in Ohio. Her name is Mary Workman, and she is showing a sample of contaminated water from her home's well, which was contaminated by coal mining in the 70s. So this is part of what was going on in the country that sort of led to the Safe Drinking Water Safe Drinking Water Act being passed in the first place. So that act was amended in 1977, 1979, 1980, and 1986. So the 1986 amendments required maximum contaminant level goals and maximum contaminant levels, or MCLs, for 83 contaminants. In 1990, the Science Advisory Board ruled that drinking water contamination was a significant environmental risk and that microbial contaminants were a significant health risk. So disinfectants are added during drinking water treatment to reduce the risk of illness from microbial contaminants, but they do react with naturally occurring organic materials to form disinfection byproducts. So later rules were added to minimize risks from those disinfectants and disinfection byproducts. So precursors are found in surface water. Examples include naturally occurring organic material from plants and animals in lakes, rivers, and streams, as well as other naturally occurring elements like bromide. These react then with disinfectants such as chlorine, chloramines, ozone, and chlorine dioxide, and then create disinfection byproducts such as THMs, trihalomethanes, haloacetic acids, bromate, and chlorite. So the stage 1 and stage 2 disinfection byproduct rules were intended to minimize risks from disinfection byproducts and the disinfectants themselves. Obviously, we need to disinfect drinking water to reduce pathogens that cause immediate illness. So things like E. coli, typhoid, cholera, crypto. But the process of adding those disinfectants creates unintentional byproducts, which can cause long-term health effects or chronic health effects, such as liver, kidney, or reproductive problems or cancer. So to minimize that, the disinfectant byproduct rules were establishing maximum contaminant levels, or MCLs, for total trihalomethanes, or TTHMs, haloacetic acids, chlorite, and bromate. So the first two groups, the THMs and HAAs are formed when the natural organic material reacts with chlorine, while chlorite is a byproduct formed when using chlorine dioxide, and bromate is formed when bromide reacts with ozone. The rules also establish maximum residual disinfectant levels, or MRDLs, for chlorine and chloramines, which were set at 4.0 milligrams per liter, and chlorine dioxide, which was set at 0.8 milligrams per liter. All right, so in the next few slides, I'm just going to go over some screenshots from the EPA Stage 1 and Stage 2 disinfection byproduct fact sheets with an overview of the rules. So the Stage 1 disinfection byproduct rule was passed in 1998. Stage 2 was passed in 2006. The rules require compliance with the maximum contaminant levels and maximum residual disinfectant levels, and an evaluation of the distribution system. Also, conventional filtration plants must remove specified amounts of organic material that can react with chlorine to form disinfection byproducts. This next table goes over regulated contaminants and disinfectants. The Stage 1 rule required compliance with a total trihalometane MCL of 0.080, or 80 micrograms per liter. You'll also hear that referred to as 80 ppb. So this is a combined value of the 4 individual trihalomethanes that are measured. So that's chloroform, bromodichloromethane, dibromochloromethane, and bromoforms. They're listed right here. The HAA5 MCL is 0.060, or 60 micrograms per liter. Which is a combined value of 5 of the haloacetic acids, which is monochloroacetic acid, dichloro, trichloro, bromoacetic acid, and dibromoacetic acid. Bromate was also regulated with a 0.010 MCL for plants that feed ozone, and chlorite has a 1.0 milligram per liter MCL for plants that feed chlorine dioxide. The MRDLs, maximum residual disinfectant levels, again, 4.0 for chlorine and chloramines, and 0.8 for chlorine dioxide. All right, this is the compliance determination. So how do we determine compliance? So in Stage 1, the values for THMs and HAAs were to be averaged across the entire distribution system over a running annual average. That's what RAA stands for. And basically that means you take samples every quarter and then you average out all of those samples over the year. So in Stage 2, they moved from an average of the entire system to being a locational running annual average, LRAA. So that means that compliance has to be achieved at each individual sampling site. And it's still averaged over the year with sampling every quarter. Bromate is calculated as a running annual average. Chlorine dioxide and chlorite have to be analyzed daily with follow-up monitoring if there's exceedances. And then chlorine and chloramines are calculated from a running annual average as well. And the DBP precursors, so TOC must be monitored monthly for the source water TOC, source water alkalinity, and treated water TOC. All right, this one table is a little bit smaller font, a little harder to see, but basically what this just shows is the monitoring frequency for both the Stage 1 and Stage 2 for the various disinfectant and disinfectant byproducts. The frequency and number of required locations to monitor go up based on the size of the population. And then as well, there's a split out between surface water and groundwater. So for Stage 1, the number of locations was based on the treatment plants. For Stage 2, it's just based on the size of the system. So it's a fixed number, with 2 being the minimum number of locations and 20 being the highest number of locations for surface water. All right, now we're going to talk a little bit about operational evaluation levels. This was something that was implemented with the Stage 2 disinfection byproduct rule. So here is how the operation evaluation calculations are performed. These must be conducted for the total trihalomethanes and HAA5 for each individual sampling location. So what it means is that you add the previous 2 quarters of sampling before the current quarter plus twice the current quarter and divide that by 4. So basically it's giving you a weighted average of your results when you're weighting the current result twice as much as the others. So if your calculation of this OEL exceeds the maximum contaminant level for the sample, the system has to take actions that are shown on the table to minimize future exceedances. We'll talk more about that later. And then finally, TOC removal. This is for conventional filtration plants that treat surface water. So the required TOC removal is based on the source water TOC and the source water alkalinity. So the higher the alkalinity, the harder it is to remove the TOC, so the lower percentage that is required. But the higher the TOC, the higher the percent that needs to be required, to be removed, sorry. So this part of the rule is to require adequate removal of naturally occurring organic material from the water during the treatment process using coagulation, sedimentation, and filtration, which limits the amount of disinfection byproducts that are formed. All right, so we got through all those really boring screenshots. And now we're going to talk a little bit more about disinfection. I'm not going to go over this into too much detail because it was already covered in previous presentations. So why do we need disinfection in drinking water treatment? How does it work? What are the disinfectants? What factors need to be considered when selecting a disinfectant? And then what is CT in drinking water? So here's a schematic of a surface water, drinking water plant process. In this process, there are several barriers for controlling pathogens. So as you can see here, we've got coagulation, sedimentation, filtration, disinfection, and storage. Coagulation and sedimentation aren't technically barriers as far as controlling pathogens, but they are important parts of the process because they make the other barriers more efficient. All right, so we need multiple barriers for pathogen control because any barrier can fail. So anywhere along this process, there are things that can go wrong. For example, not all microbes are easily filtered, such as viruses, so this filtration step isn't going to be as effective for viruses. Cryptosporidium is an example of a parasite, and it is not easily disinfected by chlorine because it can form a protective shell called an oocyst, and that makes it less susceptible to chlorination. So the cumulative effect of having all of these barriers greatly reduces the likelihood of pathogens reaching the consumer. So that's why it's important to make sure that all of them are optimized as much as possible. All right, so what is disinfection here? So disinfection is the selective destruction or inactivation of pathogenic organisms. So we're focusing on that. We're not focusing on sterilization of the drinking water because even though that would be great and would involve complete destruction of all those organisms, it would be very, very expensive. So this diagram shows how chlorine causes inactivation and destruction of bacteria. So basically what happens is the hypochlorite ions can disrupt the cell wall barrier and change the permeability of that cell for, this is like a bacterial cell. The hypochlorous acid, like Joe was talking about earlier, when you add chlorine to water, it forms hypochlorous acid and hypochlorite, depending on the pH. But the hypochlorous acid, one of the reasons it's so effective is because it can go right through that cell wall. And then once it gets in there, it disassociates into hydrogen ions and hypochlorite ions, which interfere with biomolecules and enzymatic reactions. So after that happens, cellular constituents start to leak through the cell wall, cell functions start to shut down, the cell is weakened and eventually dies. All right, so what are disinfectants that we're talking about here? Chlorine is the most common disinfectant used. Large plants often apply chlorine in the gas form. It's compressed into liquid and received in these large 1-ton cylinders like are shown. Some plants apply chlorine as hypochlorite. Hypochlorites are less dangerous than chlorine gas. However, they decompose in strength over time while in storage. So there's two types of hypochlorites used in water treatment, sodium hypochlorite or bleach, and calcium hypochlorite. So bleach comes in a liquid form, which contains between 5 and 12% chlorine. HTH, calcium hypochlorite, is mixed with water to form a hypochlorite solution. And again, that HTH stands for high test hypochlorite, in case you never heard that one before. I don't know how long I'd been in water treatment before I finally figured out why it's called HTH. So chloramines are another disinfectant that are sometimes used in some systems, not very often in Arizona due to issues with water temperature usually. Chlorine dioxide is a disinfectant. It's a strong oxidant and it's made on site at the water plant by reacting sodium chlorite with chlorine gas. Ozone is also formed on site by passing high voltage electrical current through oxygen gas inside a reactor. It is also a strong oxidant. And then UV light can be used to disinfect water. All right, so factors to consider with disinfectants. Chlorine gas, again, requires a lot of safety precautions, including a scrubber system and self-contained breathing apparatus for operators that must be worn during maintenance. Bleach is less dangerous than chlorine gas. However, it decomposes in strength over time while in storage. And that is a really major consideration. Temperature and light can break down hypochlorites before they're able to react with pathogens in water. So it's really important, especially here in Arizona, to take care not to store bleach in sunlight and to avoid high temperature storage, such as outside in the summer. If you can't avoid those conditions, try to limit how much you're going to order at a time so that it's going to be used in a reasonable period. It is really important not to store bleach past the expiration date given by the manufacturer because you don't know what that strength is going to be by the time you get to using it. If you ever have any questions, it's really best to check the strength of that bleach before you're using it to make sure that it's the concentration that you think it is, or so that you know what the concentration is. And you can do that by diluting it down to a measurable range so that you can measure it with a handheld spectrophotometer. All right, calcium hypochlorite, must be dissolved in water first. It is more stable, however, than the liquid solutions of sodium hypochlorite. Chloramines, again, we don't use these very much in Arizona. It is something that's been more popular around the country because they form fewer THMs and they decrease, the residual decreases more slowly in the distribution system, so it's more stable. But you can also end up with nitrification in your distribution system, which will degrade your drinking water quality and can cause regrowth of bacteria. So if that ever happens, it can be caused by high temperatures and high water age. It's part of the reason it's not very popular here. But systems usually have to switch back to free chlorine disinfection to flush out the distribution system if that nitrification happens. Chlorine dioxide, it is a strong oxidant, but it produces little residual and does have chlorite byproduct. Ozone, again, same kind of thing. And then UV light does not have any residual. So with these last three, free chlorine is usually used as the residual, free chlorine is also added to give a residual in the disinfection, in the distribution system. All right, so what are some factors influencing disinfection? We've got several factors. pH, chlorine infects water much faster at pH 7 than pH 8. Temperature, because disinfection is a chemical reaction, the reaction rates double with every increase of 10 degrees C. So basically it occurs much faster and more efficiently at a higher temperature. Turbidity, the higher the turbidity, the less the efficiency of disinfection. Usually this is not an issue once the water has been filtered because the particles that cause turbidity will be filtered out. Organic matter, the higher the organic matter, the less the efficiency. And that's partially because those organic particulates are going to react with chlorine and form disinfection byproducts. And then inorganic matter, also ammonia and silt, can reduce the disinfecting power of chlorine. All right, so I know Joe already talked about this, so I won't go on and on about this, but basically just wanted to point out again, breakpoint chlorination, free chlorine, which is shown here in this blue circle. It's a stronger oxidant. It is not as stable, so it decays faster. Combined chlorine mostly is made up of chloramines. Those are weaker oxidants, but they are more stable. And then the combination of both is known as total chlorine. So I just wanted to point out too, in this graph here, you can see that there's the destruction of chlorine residual by reducing compounds in the beginning. So that's that first amount per chlorine added. After that, the chloroorganics are formed and chloramines. So this is partially when the trihalomethanes and haloacetic acids are being formed, is in this part of the curve. So it's not until we get over to this part that we're actually forming free chlorine residual. Okay. So one of the main regulations for disinfection for plants treating surface water is the surface water treatment rule. This was originally passed in 1989. Further rules were passed later, including the interim enhanced surface water treatment rule in 1998, filter backwash recycling rule in 2001, and then the long-term 1 enhanced surface water treatment rule in 2002, and long-term 2 was passed in 2006. So basically this is requiring that disinfection is sufficient to ensure that the disinfection plus filtration of the plant achieves at least a 99.9 or 3 log inactivation of Giardia lamblia and 99.99 inactivation or removal of viruses. So that's also known as 4 log inactivation. So we're going to explain more about how that's calculated in the next couple of slides. All right, so disinfection efficiency required by the surface water treatment rule is measured as CT, whereas C is the concentration of disinfectant residual in milligrams per liter at the end of the segment, and T is the amount of time that the water is being disinfected in that segment based on the peak hour flow rate. So each disinfectant of whatever kind requires a different concentration and time to achieve the proper disinfection level. So if you've got free chlorine, chlorine dioxide, ozone, whatever, those calculations are going to be a little different. And again, a level of 3 log 99.9% or 4 log 99.99 is required for parasites and viruses, respectively. So here's an example of a disinfection profile worksheet that we use at one of our plants that calculates the log inactivation. So there's different segments in this worksheet for each part of the plant that could include disinfection, as well as segments for different kinds of disinfectants. So we've got one segment here for chlorine for the pre-sed. We've got one segment here for chlorine dioxide because this plant feeds chlorine dioxide. So once all of these different segments are added together, it totals them up down here to get the total log inactivation at the first customer. So this is going to be compared to the surface water treatment rule minimums at the bottom here for the plant. So this also takes into consideration engineering details such as the filtration credits that the plant receives. So I just wanted to go over all of this just to emphasize again that a certain amount of CT is required by the rules, but storing that water for too long or having too much disinfectants in the water can cause a high amount of disinfection byproducts to form. So again, just to give a recap of that, precursors in the water plus your disinfectants are going to cause your disinfection byproducts. So that's going to include your total trihalomethanes, your haloacetic acids, bromate, and chlorite. All right, so what is the natural organic matter that I keep talking about, and what is total organic carbon, and how are they different? Basically, natural organic matter is a complex mixture of organic compounds. It's going to be present in all natural environments with plants and or animals present. So here, like you can see in this picture, we've got plants. In this surface water, we've got algae growing in the water. We very likely have some fish hanging out in there and other things. So there's going to be a complex mixture of carbon containing or organic compounds. And I just want to take a moment to point out that the rest of the world uses the word organic much differently than chemists do. And being a chemist, I feel like I have to defend myself for a moment here. Organic doesn't mean healthy in this instant. It doesn't mean not using pesticides. It means containing carbon. So organic matter is carbon containing matter. So again, this comes from decaying plant material, biological processes. Can also come from human-caused activities like stormwater runoff or wastewater treatment effluent. All right, so that's natural organic matter. What is total organic carbon? So that measures all the carbon in compounds like proteins, hydrocarbons, anything where carbon is bonded to something else. Inorganic carbon is found in minerals like limestone, so calcium carbonate. So there is carbon there, but you'll note that TOC, the total organic carbon, is going to react with the chlorine to form disinfection byproducts, but inorganic carbon, like in carbonate, does not. All right, so adding chlorine to water with organic carbon creates disinfection byproducts such as trihalomethanes, THMs, and haloacetic acids, HAAs. So we're going to look more closely at those. I just want to point out that, again, being a chemist, I'm legally required to show you ball and stick diagrams of all these molecules because it's my job. So you'll note here that the trihalomethanes are methanes, so CH4, so there's one carbon and there would be 4 hydrogens with a regular methane molecule, but basically some of the hydrogens are substituted for different halogen atoms in the trihalomethanes. So we here have chloroform, which has 3 chlorines and 1 hydrogen. We've got bromoform, which has 3 bromines and 1 hydrogen. Bromo-dichloro has 1 bromine, 2 chlorines, and a hydrogen. And then we've got dibromochloro, which has 2 bromines, 1 chlorine, and a hydrogen. So that's all the THMs. So the haloacetic acids are acetic acids, like acetic acid is what vinegar is made out of. It's just a dilute solution. So they're acetic acids where various halogen substitutions have been made for hydrogen atoms. So there's monochloroacetic acid, has 1 chlorine, monobromo has 1 bromine, dibromo has 2 bromines, trichloro has 3 chlorines, et cetera, et cetera. All right, so these are the 4 regulated THMs: chloroform, bromodichloromethane, dibromochloromethane, and bromoform. The sum of these are referred to as total trihalomethanes, or TTHM. There's 5 regulated haloacetic acids, referred to as the HA5. Again, monochloro, dichloroacetic acid, trichloroacetic acid, monobromoacetic acid, and dibromoacetic acid. So there's actually a total of 9 haloacetic acids that are measured using the EPA 552.2 method, but only 5 are currently regulated. The other 4 are bromochloroacetic acid, bromodichloroacetic acid, dibromochloracetic acid, and tribromoacetic acid. The total of these are known as the HA9, and they were studied under the Unregulated Contaminant Monitoring Rule 4 from 2018 to 2021. Okay, so disinfection byproducts, what factors affect their formation potential? So there's many factors, and there's lots of studies that have been done to show the influence of these factors in forming THMs and HAAs. And they've resulted in equations like this one shown, which if you're just looking at it, you're like, wow, that's really complicated. There's a lot going on here. So we're gonna break that down a little bit. So what this is saying is DBP, which is either total trihalomethanes or HA5s, are formed by a combination of these factors. So TOC here in the equation is the treated water total organic carbon. So that is going to affect your formation. UVA is the UV absorbance. So that is a measure of what kind of carbon you have. Basically, the higher the UV absorbance, the more likely it is to form the disinfection byproducts. And just as a side note, UV absorbance is a test that can be done more quickly and easily than total organic carbon analysis. It's not really a replacement for that, but it can be used by labs that don't want to invest in a big instrument because you can get a UV spectrophotometer for a lot less than you can a total organic carbon analyzer. Chlorine, the applied chlorine dose in milligrams per liter is a factor. Temperature, or sorry, bromide concentration in your treated water. Temperature is a big effect, especially over 20 degrees C. pH, your treated water pH is a factor. Your reaction time or water age in hours. And then every water quality is going to have a different formation potential, which is accounted for by all these different coefficients. So THM formation potential, also called THM-FP, can be measured according to standard methods 5710B. It involves taking the finished drinking water, buffering it to a constant pH, and incubating it for 7 days to see how much THMs form. So this graph on the left here is conducted in a study with water from a river in Iran that has similar water characteristics to our surface water here in Arizona. This basically shows that as your initial TOC content increases, your THM formation potential increases. And also your residual chlorine, which is shown on this graph here that kind of goes down and to the right, goes down as your TOC content increases. The graph on the right shows a study that we conducted at our Union Hills plant last year. We'd been having issues with some elevated THMs, and I wanted to do a study to see what was happening in the distribution system. So the study showed that much of the THMs that were forming was happening in the first 24 hours, and it was largely due to the kind of TOC present and the amount that was present. And that had been fluctuating due to runoff in the watershed. So our raw water TOC for this study was 3.88 and our finished water TOC was 2.70. Our initial 0-hour THM was about 33.5. And you can see as the time that we incubated, the water increased, the THMs continued to increase. And then the free chlorine decreased up to a certain point. And then we actually added more chlorine to simulate boosting the chlorine in the distribution system. So after 4 days, the water had reached a really high THM formation potential. And this again was just a study just to see what could be going on in the distribution system. Okay, so we're going to talk more now about THM formation or reduction and control. So to control the formation of disinfection byproducts, we can do several things. We can control the precursors that are found in the drinking water, such as the naturally occurring organic matter. We can control the amount or type or timing of disinfectants that are applied, such as chlorine. We can reduce the water age, so basically how long the precursors and the disinfectants are in contact with each other. And we can remove the disinfection byproducts at the end or blend higher DBP water with lower DBP water before it enters the distribution system. So I'm going to talk about each of those strategies next. All right, so treatment strategies to reduce TTHM or HAA5. The first is to reduce the total organic carbon in the finished drinking water. So to do that, we can utilize additional coagulant or perform enhanced coagulation, which basically would be to optimize the pH at which the coagulation is happening. We can also use powder activated carbon or PAC, or granular activated carbon, or GAC, sometimes known as PAC or GAC. We can use the GAC filters in contactors or in filters, because the activated carbon is going to adsorb the TOC and remove it from the water. So the stage 1 disinfection byproduct rule requires a certain amount of TOC removal, but more may be necessary for THM control. So here's a table that I created to assist our process control specialists and operators in determining the amount of TOC that might need to be removed, which is often a higher amount than what is required in the regulation. So you can see here in the small table on the left that usually our source water alkalinity is usually above 120 milligrams per liter. So I highlighted this last column because this is the one we're most usually looking at. Note that in this larger table that I created here, for the lower TOC levels, the required percent removal is usually going to result in relatively low TOC levels until you reach about 3.5 to 4 milligrams per liter on the source water TOC. So if you have, for example, source water of 4.0 and you're only removing the minimum, that's going to give you a finished water TOC of 3.0, which is still kind of high for THM formation. So to reach a more reasonable target of 2.5 milligrams per liter, you're going to need to achieve a much higher TOC removal of 37.5% to get that target TOC level that you're trying to get to. Okay, the next strategy is to reduce or delay the chlorine and caustic dosage. So pre-chlorination at the influent of the plant is going to cause very high disinfection byproducts, as this is the point in the treatment process where the natural organic material, or TOC, is at the highest. So this used to be a common practice in water treatment because it can help with settling and it can help with filtration. But we now know that it's detrimental because of the number of disinfection byproducts that it forms. Something, if you still need to have some kind of pre-oxidant, you can change to one that doesn't form disinfection byproducts or as many, such as ozone or chlorine dioxide. Another strategy is to chlorinate only after filtration when the TOC has been reduced as much as possible. A third strategy would be to reduce the amount of chlorine that you are feeding going into your clear well or your reservoir, and feed only what is needed to meet CT, and then boost that at the end of the reservoir prior to your distribution system. And then finally, if you can keep the pH to a lower level, so close to 7 until prior to your distribution system, that's going to make your disinfection more effective and lower your THM formation. And after that, you can boost it to whatever you need to meet corrosion control requirements. A third strategy is to reduce water age. So it's really important to make sure that you're being efficient with your water storage. You need to keep what is needed for water pressure and fire flows without filling up every tank and reservoir. You also want to make sure that your water in each of your tanks or reservoirs has good turnover, and don't store more than is needed for your system. If you have any dead spots in your tank or reservoir, consider adding a mixer. So example, like the picture shown, if you only have one inlet and outlet, you might end up with some dead zones in that tank. So you might have to figure out a way to install a mixer to ensure good circulation. You also want to make sure you're monitoring any booster sites in your distribution system and make sure that the chlorine is not too high or too low. Okay, so another strategy that you can use is to remove TTHMs or HAAs from the treated water. So the slide that's on the left, I know it's really busy and there's a lot going on, and I couldn't fit all the information for the legend on there because there was just too much going on. But it shows some testing that we did in our process labs here in Phoenix, where we discovered that feeding extra chlorine along with the chlorine dioxide that we use for our preoxidant caused some THMs to form, and then those THMs were removed by the granular activated carbon that we have in our filters. So the blue here represents the THMs that are added to the top of the GAC media, and the green represents the THMs that are leaving the media, and then the red and yellow triangles there represent our EPDS THMs. So basically what's going on is when we fed extra THMs, some of those were removed in the media, and that overall lowered our EPDS THMs. And you can see we did a couple of tests just to make sure that this is what was actually happening. So we stopped feeding extra chlorine 2 times where these red circles are. So you can see here that the THMs that were formed prior to the media went to 0. But when that happened, the EPDS THMs that were going into the distribution system shot way up. So basically we had been getting an EPDS THM at this plant of about 35 parts per million, and as soon as we turned off the extra chlorine and stopped forming those THMs that were taken out by the media, it went up to about 55. So that was a big discovery that we had at that plant. So basically what we found out there, that if we use this mixed oxidant strategy all the time with our GAC filters, we can take THMs out when they're adsorbed onto the GAC, and they do not reform later in the process. Okay, so besides GAC media, there's other ways to remove TTHMs. Aeration or air stripping can remove volatile disinfection byproducts. So this works best with aerators like the one shown, spray aerators. Bubble aerators do not work as well because they don't have as much surface area. Only chloroform, bromodichloromethane are removed in significant amounts. Does not work as well with dibromochloromethane or bromoform, and it doesn't really remove HAAs. So when you're using the strategy, you'll need blowers to bring in fresh air, and you might need to boost your chlorine afterwards to bring it back up to an acceptable level, because the chlorine will also volatilize if you're using this. All right, another strategy that you can use is to blend water with water that's lower in TTHMs or HAAs. So you can blend treated surface water with treated groundwater, which has lower total organic carbon and lower disinfection byproducts. Another example would be that you can blend your GAC contactor treated water with non-GAC treated water to reduce your overall costs, but improve your disinfection byproduct levels. All right, so monitoring disinfection byproducts. Regulatory analysis is only required quarterly or every 3 months, but a lot can happen in 3 months. So more frequent monitoring of THMs and HAAs is recommended if possible, especially during certain conditions. Runoff from monsoon or winter storms can lead to elevated total organic carbon, which can lead to changing amounts of disinfection byproducts, THMs and HAAs, that are being formed. The high temperatures during the summer months can cause the DBPs to form more quickly, so you can all of a sudden have a spike in your disinfection byproducts. Other unusual system events, such as plants being shut down, distribution mains being shut down, or wells being offline, anything that can cause higher water age or higher than normal chlorine demand or total organic carbon. These are all things where you would want to be monitoring more frequently to make sure that you aren't having a situation in your distribution system. So Phoenix has a monitoring strategy that we use to keep disinfection byproducts under control. And just to, as a side note, we don't normally have issues with the haloacetic acids in Phoenix, except for during times of unusual runoff. One such time was during the early part of 2005 due to fire flows from the Rodeo Chetiskyi fire. I'll talk a little bit more about that in a minute. But you'll notice that most of the time when I'm talking about disinfection byproducts, I'm almost always talking about THMs. So what we do to kind of keep everything, tabs on everything, we analyze the TOC in our source water throughout our plant and in the finished water daily at our process labs. And again, this is non-compliance. This is just monitoring analysis that we do. We also analyze our THMs by GC and our chlorite by IC daily because we feed chlorine dioxide. We analyze THMs every 2 weeks and our HAAs once per month during the year at the compliance lab as well, in addition to our normal daily monitoring at the process labs. And then we send out twice weekly reports to our process control specialists and our water production management with our TOC and THM results. So here's an example of our report, basically just showing the incoming TOC as it's reduced during the various parts of the treatment process. And then over here we have our trihalomethane monitoring. So we do 0-hour EPDS THMs, and we also do a 48-hour simulated distribution system. So another part of our strategy, we send out bi-weekly reports with the THM results that are analyzed at our compliance lab to our water production process control group. And this includes process control specialists, as well as production management and our process lab supervisors. We identify any problem sites so that action can be taken if needed. And we monitor more sites than just our compliance sites to make sure that our whole distribution system is checked. So if any of our biweekly TTHM results are within 90% of the MCL, which is 72 micrograms per liter or higher, we notify various divisions in our department to respond. So our engineering team sends out flushing procedures for the sites based on modeling that they've done. Our distribution teams do flushing in the system. Our ESD teams go out and do additional sampling and reanalysis, and then production closes out the event if the results are below the threshold. So just to give you, this is a picture of what the reports would look like. And then this is also just an indication of the unidirectional flushing instructions that are sent out by our engineering group. All right, so moving on from monitoring. Now we're going to talk about reporting of the TTHMs and HAAs for regulatory purposes. Since the stage 2 DBP rule was enacted, compliance is based on a locational running annual average. So each system must complete sampling at a required number of sites as shown in the chart, from 2 to 20 for surface water or 2 to 8 for groundwater. Sampling is done quarterly or maybe annually for small systems, and then the operational evaluation level must be calculated for each site. All right, so locational running annual average, I'm just going to go through what that looks like. So for each site, you're going to add the most recent 4 quarters of THM or HAA data and divide by 4 to get the LRAA. Then we're going to compare that to the MCL, which is 0.080 for THM or 0.060 for HAAs. So for an example, if your quarterly values are 0.064, 0.078, 0.090, 0.077, you're going to add those together and divide by 4, which gives you 0.077, which is less than the MCL. So this is within compliance for the LRAA. Note, however, it's pretty high. All right, so for the operational evaluation level calculation, you're going to take your 2 previous quarters plus twice your current quarter result and divide by 4. And then you're going to compare that to the MCL. So in the previous scenario, we're going to add 0.078, 0.090, 0.077, 0.077, and divide by 4. And that gives us 0.081, which exceeds the THM MCL. So this is going to require an operational evaluation to be conducted. So You have to conduct an operational evaluation, which is an examination of your system treatment and operational practices, including storage tank operations, excess storage capacity, distribution system flushing, changes in source or source water quality, treatment changes, any problems that may contribute to THM and HAAs, and what steps can be considered to minimize future exceedances. Note that these are a lot of the things that I already talked about in those previous slides about making sure you're not storing too much water and making sure you're flushing any spots in your distribution system that could have problems, and keeping track of all those changes in source water quality, those kind of things. All right, so every quarter for the Phoenix Drinking Water Compliance Team, they're calculating the LRAAs and OELs for each site, and then they send out a map with our LRAA results. This helps us identify where we might be having problems in the distribution system. This is just a little zoom in so you can kind of see, shows each spot on the map and what our locational running annual average is at each of those sites. All right, so what are some challenges that you might have in meeting compliance for THMs and HAAs? Changing source water quality, costs of chemicals, costs, time, and staffing for monitoring, for sampling and lab analysis, reducing your TOC, and changing feed strategies. So I'm going to go over these. First of all, changing source water quality. The last several decades have brought many challenges in Arizona surface water quality. Wet winters have led to an increase in vegetation, which becomes fuel in later seasons of drought and heat for intense wildfires. So these wildfires and the subsequent runoff cause higher total organic carbon loading into the reservoirs on the salt and Verde watersheds in particular. And this is really interesting because the fires not only cause burned plant material to go into the watersheds once it rains, but they also cause the water to run off more quickly because the root structures of the plants are gone, causing loosening of soils and more soil to flow into the water. Here's just a map from SRP showing that since 2000, more than 3.5 million acres of forests in or around the Salt, Verde, and East Clear Creek watersheds have been burned by wildfires, including mega fires such as the Rodeo, Chetasky, and Wallow fires. So one of the things that I was talking about when we had HAA problems was due to this Rodeo Chetasky fire here that's mostly on the Salt watershed. So what that did was, because it was burning forest, it caused a really high amount of organic material to be burned that did cause us some challenges on the HAA side of things and not just the THM side. All right, costs of chemicals. Chemical costs have climbed at an increasing rate over the last few years. Trying to reduce your finished water TOC is becoming increasingly difficult due to rising costs, especially for coagulants such as ferric chloride, aluminum sulfate, polyaluminum chloride, and aluminum chlorohydrate. Coagulant aids such as polydadmac or coag poly, might have heard of it as, they increase your flock formation and settling efficiency, which can help you reduce your TOC. And then powder activated carbon and granular activated carbon can also be used to absorb TOC. And of course, those costs as well as chlorine has also gone up. Some THM challenges, again, reducing TOC and changing feed strategies. One of the challenges can be changing your mindset from treating for turbidity to treating for TOC or treating for THMs. And this is just something, you know, strategies that worked well in decades past don't work as well for new treatment strategies. So example, pre-chlorination may have worked well in the past for turbidity treatment by oxidizing solids, but that causes a huge spike in your disinfection byproducts. Feeding minimal coagulant to optimize filtration can keep your costs down, but it doesn't help reduce your TOC, which can cause elevated THMs and HAAs. And something that I heard a lot when I first entered the field, better hot than not when it comes to chlorine. It's not always better, especially for THMs and HAAs. So the other issue that you might have is your treatment mindset may have to shift back and forth depending on your situation. Here's an example of some runoff from flooding that's happened. So if you have heavy storm runoff, your turbidity spikes to over 1,000 NTU. you're obviously going to have to treat for turbidity first, keep the water safe, and then go back to treating for TOCs and THMs once the source water returns to normal. All right, other issues, costs and time. Staffing for monitoring takes time and staff to do sampling and analysis required to monitor THMs and HAAs more frequently than required. And just some things to think about. If the cost of bringing analysis in-house is too high, what are some other options? Could you do additional monitoring monthly for process control purposes, maybe just for your problem sites? If a nearby utility analyzes samples, can you work out an agreement to analyze your samples as well? All right, so trying to bring this in for a landing, our conclusions: know your DBP rules, understand your disinfection byproducts, reduce and control your THM HAA formation in your system, monitor your THMs and HAAs regularly, report them accurately, and conquer your THM and HAA challenges. So just for some acknowledgements, want to shout out Beret Kimball, my deputy director, Brittany Dempster, laboratory superintendent, Shauna is my water process chem 2, and then all of my staff at the water treatment plants, process control specialists, supervisors and engineers, and then SRP. I stole a lot of slides from them. So speaking of stealing things, here's my references, and you'll be able to see those on your slides. Does anyone have any questions?
All right. No questions, but plenty of praise, Allison,
Okay.
for that presentation. Thank you very much for your time. Just if anyone has questions, please drop them in the questions box or the chat box, whatever you have access to. Once again, thank you very much, Allison, for your time. And if there's any questions, we'll reach out to you by the end of the webinar, or we'll email you too for follow-up.
Okay, thank you so much.
Thank you. And just for a quick addressing of TTHMs, HH5s on ADQ side, I wanted to bring in Karen Shanafelt in our compliance and enforcement unit, just to go ahead and address what happens when you're exceeding these MCLs and how does ADQ get involved. Karen, are you available?
Yes, I'm here.
Okay,
So one thing hopefully that our audience realizes is that when a public water system is exceeding a maximum contaminant level, especially for TTHMs or HAA5s, that the expectation from an EPA level is that we put that system in enforcement. We do track all systems that exceed, but hopefully you have a clear understanding from Allison's presentation that TTHMs are a very complicated issue, a lot of chemistry going on, and unfortunately those problems don't tend to resolve themselves quickly. So in those cases, we typically go with formal enforcement, which allows that system to develop some timelines. And what we're trying to accomplish by doing that is we're asking that system to develop a corrective action plan. So there are so many different parameters that can be contributing to the TTHMs. And so we want that system to do a deep dive into what could possibly be causing it, and what are the different solutions that a system has tried. Currently, we have 4 systems that are exceeding the MCL for TTHM or HA5s, and we are actively working with those systems. We are even bringing EPA experts from headquarters to help one system that's unfortunately been struggling with THMs for, unfortunately, years. Another program that we're implementing, or we've implemented most recently, are when systems do exceed a maximum contaminant level, we want those systems to provide an alternate source of potable water to their residents so that the residents are not consuming the high TTHM water for any extended period of time. So of course, it is an additional burden on that public water system, but it's the right thing to do for those residents as we're seeking long-term solutions.
Okay, thank you very much, Karen, for filling in. Once again, thank you very much, Allison. All right, we're going to go ahead and move in to a very quick 10-minute break here. Just a little announcement, please make sure you're being very attentive to these webinars and these presentations as we're going through them. Your PDHs are pretty much on the line. We do monitor to make sure you guys are paying attention. So if you're only paying attention for 15 minutes of the entire webinar and you're claiming 4 hours, we will contact you when we start doing our PDH audits. And just in case you need to engage with us, please remember we do have the question and the chat drop down option. So with that note, let's go ahead and start our 10-minute break. We'll resume at 10:15 with our next presentation from Consor, Frederick Tack, PE with Consor. We'll see you in 10. All right, without further delay, we're going to go ahead and continue this webinar. Please make sure you're coming back on in. Let's go ahead and see. Frederick, are you prepared?
I am.
Awesome. All right, let me go ahead and send the screen power your way. There we go. Yes, right, looks like we got your note side there.
Yeah, let me switch that. How about that one?
Looks good. You ready to go?
Yeah, excellent. Thank you. Good morning, everyone. I am pleased to have the opportunity to be here to talk to you about taste, odor, and appearance regarding the aesthetics of water quality. Thank you, Ebony, for the invite and the opportunity. And thank you to the previous presenters, really set up a lot of information that I don't need to review. So we can just focus on these main aspects and how chlorination can affect and influences decisions and responses to taste, odor, and appearance concerns. So first, a little bit about myself. I've been in the industry over 23 years. I'm an engineer by education and licensure, but I'm also a certified operator and have been the operator of record and manager for a variety of water and wastewater systems. I'm a board certified water resource engineer, and I serve as the national practice leader for Consor Engineers. What we're going to talk about in this short period of time, some basic learning objectives, go over some introduction to just some familiarity with the concepts related to aesthetics and water quality, talk about what those common aesthetics are and what the regulations are around that, talk about the sources to be considered, and then what is the actual impact on chlorination and those decisions regarding aesthetics and water quality. And then finally, what are some techniques to control some of those concerns, mainly post-chlorination. So the learning objectives for today, I hope to be able to share with you is one, that you'll have an increased understanding and ability to explain the importance of aesthetics, have a better understanding of that, and how chlorination impacts those aspects. Two, to help enhance your awareness of the standards set by regulatory agencies like US EPA, focusing on aesthetic criteria. And finally, an improved comprehension of the techniques to control and improve aesthetic quality post-chlorination. All right, so what is the importance of aesthetics? Really, I'm going to focus on these three things: taste, odor, and appearance in drinking water. Why is that important? First, for health and safety. Second is consumer confidence. Can be an indicator of potential risks, and to meet certain regulatory requirements. This picture seen here on right is something none of us want to see, but this is an exaggeration of what these aesthetic concerns can help mitigate. So although chlorine is essential for disinfection and providing residual and distribution systems, it can also negatively impact certain aesthetic qualities and potentially lead to consumer dissatisfaction or impact water quality in other ways, even when contaminant levels are within regulatory limits. So just some familiarity. Allison covered some of the regulation. I'm going to double down on some of that, but there's the National Primary Drinking Water Regulations that look at about 88 different contaminants. And there's also the secondary National Water Quality Standards, which are set for 15 contaminants, which I'll talk about. The EPA does not enforce the 15 contaminants, although with a caveat, there is some reporting requirements on some of those. And they also continue to monitor 30 unregulated contaminants. The image on the right is just an excerpt from the primary drinking water standards and what those maximum contaminant levels are. But what's important here is in the legend, these are the different categories of how national primary standards are categorized. When I'm thinking about aesthetic concerns with chlorination, I'm focusing on these items: disinfectants, disinfection byproducts, microorganisms, and organic chemicals. So there are primary drinking water standard contaminants that can contribute to some aesthetic concerns. Additionally, though, there is the secondary standards. This is a table and breakdown of those 15. So these are ones that are not enforced, but as a guideline, and again, for aesthetic concerns. And some of these may also have primary standards at higher levels are not safe. What you'll notice in this table is you can actually sort these pretty much by these three factors: appearance, taste, and odor. So here's the ones that are relevant to appearance. So my first thought, if in a distribution system I'm having an appearance problem, there's something wrong with the way the water looks, this is one place I can start. I can look to see, test for these contaminants. Are these points of concern something I can optimize? Is it a taste concern? Then there's different ones I might want to look at to be able to identify, is there some contaminant that might be out of range for that, for secondary quality? And then final, a few other for odors. Now, these aren't the only factors, but it's a place to start and just the awareness and familiarity with what that is. And specifically on appearance related, if it's the color of the water, it might indicate actually which contaminant might be present. And also based on the type of taste or odor, that could also help you define and identify what's going on with the water or the system. These are what I would consider the relevant drinking water regulations for U.S. federal drinking waters, but thinking about chlorination and aesthetics, I would really focus on these. Again, not looking for you to memorize or read through all these, but I'm really concerned about disinfectant and disinfection byproduct regulations, long-term surface water treatment rules, and the national primary and secondary drinking water standards. Just as an overview of what type of disinfectants are typically used, so we're talking about the same thing. There are primary and secondary disinfectants. EPA really identifies primary disinfectants of those that are delivered before the water enters the distribution system, and secondary disinfectants are those applied in the distribution system. Common ones are chlorine, chloramines, chlorine dioxide, ozone, and ultraviolet light. Noted that some of those, like ultraviolet light, is not going to help you provide any residual for free chlorine in the system, but it can help disinfect. So just be aware of that. Some of the key things to think about when it comes to surface water treatment requirements, if you have that type of system, there's certain requirements for minimum log reduction for removal or inactivation of bacteria and viruses. So the surface water treatment rule requires a 3 log reduction and a 4 log reduction of those certain viruses. And just to define for those who maybe aren't familiar with what that log reduction actually means, an example I'd give is a 1 log reduction would be 90%. A 2 log reduction is adding another 9, so 99%. A 3 log reduction is 99.9%. And again, you add another 9 for a 4 log reduction, 99.9% reduction. So surface water treatment rule also requires a secondary disinfection to provide an additional barrier against microbial contamination. So based on the type of water you're producing and the type of disinfection that's being applied, that is going to have influence, or potentially could have influence, if you have aesthetic concerns. What you're looking at with that virus inactivation with chlorine is that log reduction based on the different pH range of what you're going to get out of that free chlorine, as shown at that table there at the bottom. So some of the takeaways from this I want you to think about is that the primary drinking water regulated contaminants can contribute to aesthetic concerns directly through disinfectant, disinfectant byproducts, microorganisms, and organic chemicals. And these things can get exacerbated when chlorinated. Secondary MCLs can affect aesthetics and also can be exacerbated when chlorinated. And that health and safety, customer acceptance, issue indicators, and regulatory requirements are important factors when considering aesthetics and water quality. And just because I'm going to focus on appearance, taste, and odor in this presentation, there are other aesthetic concerns, which I'll mention, but these make up the majority of those concerns. All right, so some good looking coffee there. I think they made it wrong. But so some of the common concerns, the US EPA will actually group these into these three categories. One is aesthetic effects: taste, odor, doesn't look right, doesn't smell right, doesn't taste right, as seen in that photo there. Cosmetics effects are those it's still a non-aesthetic effect, like it might corrode or discolor hardware, silverware, appliances, clothing, things like that. And then there's the technical effect, things that actually interfere with the ability for certain treatment technologies or equipment to work or be successful. Really looking at why each of these aspects matters, think about taste first, right? People discuss, taste can significantly affect how people trust that water, and an unpleasant taste might actually imply or perceive that it's not safe, even if it is. So that's one of the first senses. The second is odor. Think about the things we smell before we eat or drink, something out of the fridge, a certain drink, same effect with water. But that odor can go two ways. There's good evidence that some people will smell a chlorine or chemical type smell, and they might be reassured, thinking that the water is disinfected. As Joe mentioned in the earlier presentation, we're aware that actually that smell is probably identifying that there's not enough free chlorine and that there's ammonia present. So that's having the converse effect. But others also perceive that smell and are concerned about that, or may feel the water has been compromised. But I think foremost is the appearance. So color, most of all. If you see something that is off-putting in the color or appearance of water, it's turbid, has a color to it, that's going to affect your other senses before you even smell or taste it. So a lot of times appearance will influence a negative response to those other senses, even if that perception's not there. Although it's essential for disinfection, chlorination can amplify certain aesthetic qualities. So just like I mentioned, adding that chlorine type taste, which can add to that distrust, can add to the production of byproducts. And disinfection byproducts can actually have their own taste and or odor issues that are unappealing. And then residuals to taste and threshold. There really is a balance between the residual and chlorination that's needed versus any type of aesthetic concerns that might develop from that. So moving on to odor, that distinct odor of chlorine, but also lack of free chlorine is something that can be easily indicated. Excuse me, many times chloramines might be used as an alternative and can be used to address some of those odor issues, but there's other concerns with that as well, and tend to produce less notable odors, but still may have that chemical smell. And again, byproducts, disinfection byproducts also have their own unique odor from that. When it comes to the aesthetics, the visual part of it, chlorination typically improves the clarity of water, one, by inactivating microbes that might add to turbidity or cloudness, but it can also oxidize other things like iron and manganese if it is present in the water, which can cause it to precipitate. And that can either make it more turbid or less turbid. Also keep in mind some color changes. Chlorine reacts with natural materials like metal ions and manganese, which that can cause a discoloration, specifically based on the contaminant that it is. It could make it yellow, red, or brown due to that oxidation, and it can create the impression of contamination, although it may meet all required levels. And other concerns, of course, with particulates and sediments, if you're having that turbidity, chlorine can actually dislodge some biofilms that might be present in water systems or in the distribution system, causing temporary cloudiness. That might just be an indicator of flushing or cleaning that's needed, not necessarily something microbial or bacterial concern with the water. But chlorine's been shown to actually lower the color of waters and can be used to correct some color issues, especially when traditional coagulation and filtration fails. Chlorine can help that. Adequate free chlorine residuals can help clear the look of water by bleaching the organic matters. It also removes most effectively between pHs of 4 and 6.8. And high-colored, low turbidity waters are usually either naturally acidic or so lightly buffered that the application of chlorine may be sufficient to reduce the pH to the optimal range. Thankfully, Joe went over this curve, the breakpoint curve, and just identifying that insufficient chlorine dose and not reaching that breakpoint can lead to both disinfection, residual issues, but also some odor and aesthetic issues. So it is important to understand the amount of chlorine that's needed, of having a minimal amount, but not too much, and to be aware, color effects from chlorine are not temperature dependent, and typically that correction happens instantaneously when applied at the right level. So what are some of the sources of taste and odor concerns in distribution systems? So number one, and I don't want to say it's the most, but one of the most prominent is emissions from system materials or construction. So that is the leaching and or release of unwanted contaminants from the materials in the actual system itself. One of the first places we start is looking at storage tanks, where they may have an internal lining. That lining can deteriorate or corrode over time if it wasn't cured properly. VOCs or other things might leach out of that epoxy type coating and can be a source of some taste or odor issues. Other places where it's leaching out of the material is with in the right pH, we can actually dissolve or precipitate either organic matter or actual physical matter from materials into the water, which can add a metallic and or a biological type taste or odor. Also, external contaminants can be a source of that, whether it's coming in from a leak in the pipe, cross connection, or other external, pipe break, other external sources as well. There's also biological activity, which typically is going to happen in anaerobic conditions. So that's where there is maybe sediment build up in a pipeline, in a storage tank, in some sort of transfer vault. In those anaerobic conditions, there's a variety of different microbial transformations that can happen that can both propagate or grow more biological components and add to aesthetic concerns. This also can lead to the loss of chlorine residual. So when this happens, that biology is going to start to consume some of the chlorine, which is then going to propagate and promulgate more biological growth. Disinfectant residuals, also part of that source, can add to taste and odor issues. And typically that has more of a medicinal taste, and it's especially prominent when iodine or bromine are present, or total organic carbon, or algae is present. So rechlorination is important. That secondary disinfectant can really help reduce that. There are also synthetic sources. So even micro quantities of these can contribute to that. So here's a list of some of those synthetic sources. Again, if I've gone through my secondary list, I've determined based on the result from the quality of the water that I don't think it's microbial, or I don't have a sediment deposition problem. I might start looking at some of these items. So these synthetic sources can propagate odor and taste concerns as well. Next up here, I want to take a few minutes, maybe 5 minutes, to walk through is hydrogen sulfide. This is pretty difficult to have a potable water source that's free of taste and odor if you have hydrogen sulfide in the system. So you'll know it when you have it, and then getting it out is important, but it is one of the most troublesome compounds. These occur mainly in well waters, but can also be present in surface waters, usually that happen through where groundwater intrusion gets into the system, or where groundwater and surface water are blended. Things to think about on the consumer side, where you might be getting the complaints on smell or odor. Depending on what their issue is, a lot of times they're going to see these issues with their hot water heater, or say like a dishwasher or somewhere around those kitchen. If they have a sulfate reacting bacteria, they're going to have some decay in their system. They can also get an odor from that as well into their water system. So the sulfides in systems are usually produced through chemical and bacterial reactions under an anaerobic condition, very similar to the buildup of sediment and other materials in your pipelines. Sulfates can be reduced to sulfides by organic matter, and metallic sulfides can be converted to H2S by carbonic acid. So these really function at this pretty narrow range of 5.5 to 8.5, and hopefully your distribution water is going to be within that range. So you're not going to be able to, once the water's in this system, really change that pH to a level where you can adjust that easily. But the minimum detectable concentration of H2S in water is about 0.05 milligrams per liter. So if you have a sample result and you notice it's below 0.05 or far below that, that might not be the source of that taste and odor, because you wouldn't be able to perceive that. But above that, that's definitely possible. Other things like H2S, it will, in the home, in the workplace, it'll turn silverware black. It'll make, it'll stain fixtures. And typically this also can, H2S can occur in very cold water. So in raw water systems that are very cold, typically that can lead to more anaerobic conditions and propagating more hydrogen sulfide. So of course we could remove this during treatment before distribution through aeration, chlorination, coagulation, filtration, softening. The chemistry of all this is complex, but this figure represents what constituent the sulfide is in based on the pH of the water. So we see that when the pH is lowest, say 1 to 5, that dark line on the left, that's when we're having the majority of a hydrogen sulfide species. So if you have hydrogen sulfide, it's generally in your system, it's going to measure near your pH. So if you're measuring you know, a portion of it, it's going to be in this range where it makes up 0.5 to 0.6 fraction of the amount of sulfides in the sample. We get above 7 and we transition to a bisulfide or an HS minus ion. And then ideally, once we get above that, or not ideally, but once we get above about 13, we end up with just a sulfide. So it also, that helps us identify how much chlorine is needed, and we can use that information to help us understand how to remove that. So what happens when we have chlorine in water where there's sulfide as part of that? We end up with colloidal-free sulfur. That will actually change the color or add to turbidity. It can also look kind of blue. It's called the Tyndall effect, and it can be removed by filtration. Other reactions will produce polysulfides, which must be treated to prevent that odor in the finished water. But the best way to completely remove H2S is through oxidation with chlorine. So again, there will be some limitation to how much you can have that in the system, so that primary disinfection or chlorination is important if there is sulfides in that raw water or in the treated water. A pH above 9, also polysulfides can't form, but of course we don't want to distribute water at a pH above 9. And the most important factor I've found with removing H2S, if that is an aesthetic concern that you come across, is the contact time. There really needs to be adequate time for that chlorine to interact with that hydrogen sulfide to oxidize it. So there can be a case where you might increase your dosage, but still are having those odor concerns. It might be a time issue of not having sufficient contact time. But with raw water of a concentration of 5 milligrams of hydrogen sulfide, typically on the treatment side, aeration followed by coagulation filtration, plus your primary disinfectant of up to 0.35 milligrams per liter, should be able to completely remove that H2S. This is also why secondary chlorination or disinfection in the system can be very helpful if this is a persistent problem that is prevalent in your source water from a well or from your surface water. Then that secondary disinfection is a good fit. All right, some of the advantages and disadvantages of different disinfection or chlorination processes. I really just am putting this on here to identify those that address aesthetics. So with chloramines, it can have less of a chlorine taste, but as you're designing it or operating it, the chlorine to ammonia ratio gets very specific. So with that type of chlorination, if the chlorine ammonia ratio is too high, it can cause taste and odor problems. So that is probably one of the first things I would check if I'm using chloramine. If it's too low, it'll lead excess ammonia, and you actually get more of the chlorine odor from that as well. Things about chlorine dioxide with disinfection. It's very good for controlling taste and odors. It can be a lower cost to implement, but the chemical or long-term cost can be higher and the need to generate it on site. So here's some of those contact concentration times for disinfecting. And again, I mentioned it's that duration or that time of concentration that's really important on the aesthetic side for knocking down a lot of different aesthetics in addition to the disinfection quality. The takeaway here is you'll notice for chlorine, the number shown is the contact time, so the concentration times the time, contact time that's being applied. So for a temperature of, say, 15 C at a pH of 7, we have a result of about 91 milligrams per liter per minute or by minute. Where if we look at some of these other options, ozone, chlorine dioxide, it's a much lower number. So that's less dosage for less time to have the same disinfecting requirement. And as you can see, chloramine has a very high value for that. So some of the takeaways from that: chlorine can react with organic compounds naturally that are present in water and create additional taste or odor issues. 2, while chlorination effectively kills pathogens, it also can produce disinfection byproducts, and that can contribute to taste and odor problems, especially at high chlorine levels. 3, chlorine bleaches can effectively remove medium to high levels of hydrogen sulfide, and chlorine and bleach oxidizes the hydrogen sulfide to eliminate the odor and also reacts with iron and manganese and disinfects water supplies. All right, so bringing it here, the home front, what are some techniques to help control and improve aesthetic qualities? So first is managing chlorine levels, balancing that chlorine dosage to ensure you're getting the right disinfection going out the door from primary treatment and that residual in the system, while not overwhelming taste or odor impacts. Again, as mentioned by Joe, we get too low a free chlorine residual, we can end up with a high ammonia smell in the water. And of course, too high as well can influence the creation of disinfection byproducts, which can have its own taste and odor problems. 2, you can always consider the use of alternative chlorination methods, more than one, a different one. As mentioned, they each have different effects, and some of the alternatives have less taste and odor or aesthetic concerns. There's advanced treatment techniques inside the plant before you get into distribution. Things like carbon filtration, aeration, and other methods can be used to help correct odor or aesthetic issues in the distribution system. And overall, the thing I probably promote the most is just good distribution system management. Monitoring, both yourself and feedback from consumers, regular flushing to keep potential turbidity and sedimentation that could lead to anaerobic conditions and the development of biology. So that would, the biofilm control is maybe some secondary disinfection or residual in the system. And these are some of the major techniques to that. So having a monitoring location, where am I monitoring in my system? If I have a small system, maybe it's 1 or 2 locations. If it's Allison Systems, I think she has, I don't know, hundreds points. What water quality parameters are you evaluating? If you have some of those aesthetic concerns, I'm going to focus more on some of those secondary requirements and some of those odor forming contaminants to identify if any are getting too high. How am I managing that information? And then what's my plan to investigate and respond to that? Having a procedure for that. 1, it helps you plan and your staff plan for the time and commitment to do that. 2, it helps you communicate to leadership or stakeholders of when this happens, this is our process to do that. And therefore you have some defined procedure to check the box off of eliminating sources or causes to aesthetic concerns to get to what you need to correct. Other things to consider is the point where you add chlorine. So there's pre-chlorination where you're adding that in the raw water before treatment and or inside the treatment system. There's primary chlorination where you're chlorinating before it gets sent to the distribution system, or finally secondary chlorination. Each of those can have a different effect. Pre-chlorination can have other negative concerns. So it's usually not recommended as the first point, but the balance of these 3 items can really help manage and mitigate some of those aesthetic concerns. We talked about optimizing the water treatment process. You can optimize the dosage. You can optimize where you dose. Again, try to avoid pre-chlorination if possible, and ideally also reducing the water age in the system, just improving the quality of that residual. So some of those takeaways. Turbidity is important. Ideally, less than 1 is preferable. That will really help reduce the potential for aesthetic concerns. Where not achievable, less than 5 should be the target. Minimum contact time for disinfection, at least 30-minute contact time where the residual chlorine concentration is greater than 0.5 milligram per liter and the pH is less than 8. A pH, ideally less than 8. Above 8, chlorination should still be practiced, but higher dosage is typically used. And optimizing primary chlorination dosage to maintain the lowest effective level to minimize taste and odor issues while ensuring residual disinfection is key. Excuse me. So in summary here, we'll wrap it up. Chlorination is a powerful tool for protecting public health, and it can influence the aesthetics of drinking waters in ways that affect consumer satisfaction or even health and safety. Understanding what the resulting water quality aesthetics indicates regarding the performance of water production or treatment or distribution can really help you manage your system better. Chlorination and disinfection decisions can impact the quality of the conditions in the distribution system, right? Changes to how or where or what you're disinfecting can have a key impact on the distribution system regarding aesthetics. But having that feedback system of what the conditions are in the distribution system back to the production can really help you make the best decisions for your system. And with that, I will conclude and turn it back over to Ebony.
Thank you very much, Frederick. We don't have any questions posted right now, just a few thank yous. And thank you very much for your time today. If there's any follow-up, we'll follow up with you or contact or connect you with the attendee.
Thank you.
Thank you. All right, so we're gonna go ahead and move on. Sorry, it's all fast paced, but we do want to respect your time. You only have 4 hours to get all of this information out to you. Karen, are you prepared?
Yes, I'm here.
All right, I'll go ahead and send you screen power. Perfect. All right, we see your calendar, but there we go, presentation.
Okay.
Good to go.
How does that look?
Looks good.
Perfect. Okay. Good morning, everyone. Today I'm going to give you a little bit of a reprieve from the chlorination talk, although I will be touching upon that in my presentation as well, but I'm going to be talking about hauled water. Just a little bit about myself. I am a unit manager here at ADQ. I manage the inspections, compliance, and enforcement unit. I also have managed the engineering and technical assistance programs in the past and have been at the agency for over 7 years. Prior to that, I was in private industry for many years, and I'm originally from the Midwest and went to school in the Midwest. The agenda for today, I do want to talk about hauled water. We'll do a rule review. It is a very short section in the rules, but we'll go over it section by section. I will follow that up with tips for commercial haulers. Some of you may be involved with that or assisting public water systems in that. Tips for those systems that receive hauled water, what you should keep in mind. And then also tips for personal haulers or folks who are not connected necessarily to a public water system, just some things that they should keep in mind as well. At the end, if there are any questions, I'm happy to address those as well. So we'll jump right into the rule review. So the rules that govern hauled water are contained in the Arizona Administrative Code, R18-4214. And it starts out with all hauled water for delivery to a public water system shall be obtained from a source that is approved pursuant to 18 AAC 5, Article 5, or a regulated public water system. So that's a mouthful, but basically what it means is the water needs to come from a public water system if it is going to a public water system. I'm going to dive into that reference just a little bit more there. So 18 AAC 5 Article 5, or again, it's an Arizona Administrative Code reference, R18 Chapter 5. It's a section that deals with the minimum design criteria for public water systems. There are 9 sections, but on the slide, I've just kind of highlighted why it's important that that water is coming from an approved source. So as a public water system, when you're developing a well, there are certain setbacks that you need to take into consideration. One being that the well needs to be at least 50 feet from a sewer main, unless there are other accommodations that are made to that sewer main. You also want to make sure that you're at least 100 feet away from your septic tank or that dispersion field for your septic system. If a well is sited too close to a septic system, what you may encounter is infiltration of that wastewater as it percolates down into the aquifer. You may see elevated levels of nitrate. Obviously, that setback again is just a minimum. We'd like to see a greater distance when possible. The key here also for an approved source is that a public water system needs to run a new source analysis before they're able to serve that water. Basically, it requires the system to test for all the safe drinking water contaminants, over 100 of them. It covers the inorganic compounds, the semi-volatiles, volatiles, radionuclides, your microbiological, and some general water quality parameters, asbestos, etc. It's a pretty comprehensive analysis, and it tends to take 4 to 6 weeks on average, but it gives us a great baseline understanding of that water quality. Now, of course, water can change over time, but some key contaminants that we're particularly looking for are arsenic, nitrates, totocoliform. Within the state of Arizona, we do unfortunately have elevated levels of naturally occurring arsenic. Nitrates we struggle with as well, tend to be from anthropogenic sources such as agriculture or septic systems, like I just mentioned above. And then totocoliform, obviously we want to make sure that that water is healthy to drink and does not contain any acute contaminants. This section also, generally speaking, discusses the permitting process for the public water system so that it ensures that that well was properly designed by a professional engineer. So jumping back to the hauled water regulations, the second portion of that rule says that all the materials or products that come into contact with the water shall comply with R18 4213B, which basically says that the materials need to be NSF 61 certified. So as a public water system, you're most likely familiar that your chlorine typically needs to be NSF 60 certified. So 60 is for the chemicals that are added to the water. 61 covers the materials or products that come in contact with the water. So we want to make sure that you're using appropriate materials that wouldn't negatively impact the quality of that water. The third and fourth aspects of this rule is that if you're going to haul water, that truck does need to have a roof hatch, and it shall be fitted with a watertight cover, which typically implies a gasket. The roof hatch will ensure that that tank can be appropriately cleaned. We want to make sure that there are accommodations for the cleaning of that tank. And again, hand in hand with that, we want to make sure that there is a bottom drain valve that would allow for the drainage of that tank as well. The fifth aspect is that we want to ensure that all the hoses that are used to deliver that drinking water are equipped with a cap. and it shall remain capped when not in use. And that's just, again, to protect the quality of the water, to prevent any kind of contaminants from getting into the water while in transit or while it's offloading, or any other scenario like that. And so here is where this kind of connects to the rest of the presentations that we've had this morning in regards to chlorination. And when you're hauling water, the water hauler shall maintain a residual free chlorine level between 0.2 milligrams per liter to 1 milligram per liter. So hopefully you've realized that we've been talking about residual chlorine in all of these presentations. You want to make sure that that level is in the water while it's being transported, but you want to make sure that the chlorine is added at the time the water is loaded to the container. So a couple things to consider there. The system where you're receiving that water or pumping that water from, you need to clearly understand whether that water's already been chlorinated or whether you as the hauler need to chlorinate it. If it's already been chlorinated, you need to test that first before potentially adding any additional chlorine. The residual free chlorine level needs to be measured each time the water is offloaded as well. So you're basically measuring the chlorine while you're loading it and then while you're offloading it. And that hauler would need to maintain a log of disinfection, how many times he's offloaded, and those residual free chlorine measurements. And you need to make sure that you're maintaining those logs for at least 3 years. And here again, a picture of a chlorine test, a HOC meter that would give you a quantitative measurement of chlorine. We don't want to see water haulers using any kind of strip test or any kind of pool chlorine color indicator strip test. Those are not appropriate. Not appropriate for potable water. You can use that for your pool, but not in this instance. And then here, the next section of this rule says that the water transport container shall be clearly labeled for drinking water use only, potable water. We want to make sure that that truck hasn't been used for anything else that could, again, potentially cause contamination of that potable water. You want to make sure it's clearly labeled so that there's no confusion in that regard. So just some tips for commercial haulers. As a commercial hauler, you want to make sure that you understand the rules. I've just outlined the state rules, and again, they're short and sweet, but you also want to understand if there are any hauling regulations within your county. To the best of my knowledge, Maricopa and Coconino County do have their own hauling requirements as well. So if you're a water hauler, make sure that you reach out to the counties and have a clear understanding of the licensing that might be involved and inspections that could be involved as well. As a commercial hauler, obviously we want to make sure that you're cleaning and disinfecting your trucks on a regular basis. You want to maintain a sanitary condition there, again, to ensure that the water that you're delivering is healthy and drinkable. Again, you need to make sure that each load is disinfected. Either you're already pumping disinfected water or you need to disinfect it. You should be carrying that chlorine test kit with you. Again, no pool test kit. Make sure that you know how to use the chlorine test kits, that it's calibrated appropriately, that your standards are not expired, making sure that you can take those measurements and log those. You need to keep a daily disinfection log. And as another recommendation, it's a good idea to keep water quality reports from your sources. So if you're hauling water from a community water system, that system is required to create a water quality report, or sometimes otherwise referred to as a consumer confidence report. Those reports do contain a lot of great information regarding the source of that water, whether it's surface water, groundwater, a spring. It should identify if that water is being treated, and then if there are any contaminants in that water, what those levels are. So if you're not familiar with that, just reach out to ADQ. We'll help you find water quality reports. If you're hauling water from a system that's not a community water system, but rather a non-transient, non-community, or a transient system, you don't necessarily, you won't have those water quality reports, but there should be sampling and monitoring that's going on, at least for acute contaminants. And you should have an understanding or ask for copies of that analytical or know how to look that up online as well. So yeah, to have a clear understanding of the source of water and how it's being treated. Again, Coconino does regulate water haulers, so make sure you go online or reach out to the county to understand their additional requirements, as also with Maricopa regulates water haulers. Here is a quick and sort of short and sweet guideline for commercial haulers in regards to disinfection. Again, you need to understand chlorination as was presented earlier this morning. But this gives you an idea that you're dealing with ounces when it comes to chlorination. So for instance, if you are hauling 5,000 gallons of water and you're looking to have a desired residual chlorine level of 1 part per million, and the strength of your chlorine solution is 5%, you're literally trying to add 12.8 ounces. So don't just willy-nilly pour in a quart of chlorine bleach. You need to gauge that, measure. If you're unsure, always add a little less, always a little bit more can be added afterwards, but you obviously can't take it away after, once it's been added. So this is a guideline, is not, it may vary depending on the strength of your chlorine. And again, as mentioned earlier this morning, depending on the age of your chlorine, that strength may have gone down as well. So just a little guideline. And of course, you want to make sure that, like I mentioned earlier, you're chlorinating as that water is being pumped so that it has adequate contact time as well. So here are some tips if you're receiving hauled water, and normally a system that's receiving hauled water, normally that would be considered on an emergency basis. Perhaps your well pump has failed, or you're doing some major repairs where you need to haul water. It is something that we look for in emergency operation plans, that you have an understanding of who you would call and have an understanding of what that would cost that system if that emergency were to arise. We do have a couple of systems that I'm aware of that use hauled water on a consistent basis. It does get costly depending on how much you need to deliver, but normally hauled water is, again, for emergency purposes. Again, if you're receiving hauled water, you too should understand the rules and regulations. You have the right to ask to see those disinfection logs and make sure that the driver is doing what he or she needs to do to keep track of that. Again, you should be, as the receiver of that water, asking for those water quality reports and having an understanding of the source of that water. Have an understanding if that water's been treated or not. Is it just being pumped out of the ground into a standpipe, or is it going through an extensive treatment system? I would recommend taking a walk around the truck to assess the cleanliness. A lot can be said for even the exterior of the truck to assess whether that driver is concerned with cleanliness and keeping everything sanitary. And then you, as the receiver of hauled water, make sure that you have an appropriate tank or receptacle that is also clean and maintained appropriately so that you're not contaminating the hauled water that you're receiving. And do your best to ensure that that water is not stagnant. Obviously, we want to make sure that we keep water moving. If small restaurant, I know there are a couple small restaurants in the state that received hauled water. You want to keep that on a regular basis. Hauling water once a month is really not advisable. You want to be doing it on a much more frequent basis so that that water just doesn't sit, especially in the heat. And again, it's smart for you to be able to measure those residual chlorine levels as well to ensure that that residual is being maintained even over time. And so tips for personal haulers, and what I mean by a personal hauler is if you live in an area that's not being serviced by a public water system and you don't have your own private well, you may need to fill a tote in the back of your pickup truck to fill up your own cistern or what have you. We do have an infographic that I can share. I'll provide to Ebony. She can put in the presentation slides as well. I've just kind of broken it up here into two slides, but these are some guidelines if you're transporting and storing your own potable water. Normally you want to make sure that you have at least 1 gallon of water per person per day for drinking. In the summer or during the hot season, you want to probably up that even a little bit more than 1 gallon. If you're filling a container, you want to make sure that you're using either a food grade water storage container, and food grade storage containers typically meet the same parameters as the NSF 61 guidelines that I mentioned earlier. Don't refill containers that didn't originally contain water. Again, you just want to be real cognizant of that. The container that you're filling should have a nice tight lid on it, not be made of glass or anything breakable, and then having a narrow neck or opening so that that water can be poured appropriately. So if this is a situation where you're constantly hauling water, definitely worth the investment of either a tote as shown here, or small water containers that are a little bit more manageable, but make sure that you do invest in good containers. The second portion of that infographic talks a little bit again about making sure that your containers are properly sanitized. Unfortunately, I've seen people that are hauling their own water in totes, and I can literally see slime on the top of that, or you need to make sure that you're cleaning your containers appropriately. Wash with soap and water, rinse it well, and then again, you can use a bleach, a non-scented and unscented chlorine bleach solution, and here are some of the guidelines to help you do that appropriately. Make sure that you're sanitizing the interior of that container, you're shaking it well, or spraying it within that tote appropriately, letting it sit to have that chlorine kind of do its thing, and then let that, rinse that container, let it air dry before use, and making sure that you do that on a consistent basis so that the water that you're receiving stays free of contamination. Also, it's a good idea to label your containers as drinking water so that everybody's clear on what's contained in that container, and also a storage date. And here it indicates, and this is straight off the CDC website, that you want to make sure that you're replacing that water at least every 6 months. In my opinion, I would do it much more frequently, making sure that you're rotating and using that water, and trying your best to keep that water in a cool place between 50 and 70 degrees. I realize many parts of Arizona, it's impossible to store water outside during the summer and try to shoot for that temperature range. But if you have, perhaps if you're storing a tote outside, consider putting a shade structure up or something to keep that container out of direct sunlight. The sun will obviously burn through any kind of residual chlorine that you might have had in that container. And then it's always good practice to keep that water stored away from any kind of other toxic substances. Make sure you're not storing any kind of chemicals, diesel fuel, anything near water in the event that there's some sort of cross-contamination. And I think that is the end of my hauled water presentation. If there are any questions, I'm happy to address them.
Excellent. Thank you very much, Karen. We do have one question here from Paul. My understanding is bleach must be AANS or NFS approved. So adding a 5% Clorox or similar bleach picked up from the grocery store is not allowed. Can you please confirm? Oh, did we lose you, Karen?
Sorry, I put myself on mute. Unscented chlorine bleach would be considered acceptable. Make sure it's unscented if you're hauling water. If you're able to use the same NSF 60 chlorine that we see at public water systems, that is much preferred. But again, making sure that you're watching those quantities and taking those measurements.
Excellent. Thank you very much. If there are any more questions, please feel free to put them in the questions box. You can also insert comments. We read them all. All right, thank you again, Karen, for your time. All right. So we're going to finish up this webinar, bringing back Joe Cornejo, who's pretty much laying down the foundation for pretty much all the presentations you're seeing today. Joe, are you available?
I am, yeah, I'm still here, Vinny.
Awesome. Passing the screen to you.
Okay. Okay, does everything look good on your end?
Looks good.
All right, great. Okay, gentlemen, everyone who's on who's online, we're on the home stretch. This last presentation has to do with waterborne diseases and distribution systems. Now, sometimes when we think of waterborne disease, especially when we hear the word disease, we're probably thinking about bacterial and viral caused diseases, although that's one of the main contributors to maladies, physical ailments, diseases in humans and distribution systems. There's other things too. One of our earlier presenters talked about trihalomethanes. Trihalomethanes cause a specific type of disease also. We're going to briefly touch on that. And I'm hoping with the time allotted, we'll be able to cover the different types of diseases caused by water quality issues in the distribution system. And this is what this presentation is all about. Look at this next slide because it has a really interesting graphic. This has to do with waterborne outbreaks. Now, it's not talking about viral or pathogenic type outbreaks. It's talking just about waterborne diseases caused by distribution systems. I'm going to leave verbatim what the bullet point here says right next to the graph. It says decreasing numbers of waterborne outbreaks reported per year since 1982. That means that it's been going down, and that's a very good thing to see. I mean, everything that the regulators have put into place to protect public water systems has been working. But this is interesting. It says, but you see an increasing percentage attributable to distribution system issues. So overall, as an industry, the water industry has seen a decrease in waterborne outbreaks, but we've seen an increase in distribution system type of outbreaks. So what happens in distribution systems that can cause some of these outbreaks? We're not going to specifically talk about how what we can do to eliminate specific disease, but we're going to talk about the different diseases that are caused in distribution systems so that we become aware of them. And then once we become aware of them, that's part of the battle in helping to reduce them. So let's talk about, first of all, bacterial and viral diseases. These we've already heard mentioned that, like Cryptosporidium was mentioned a little bit earlier. Cryptosporidium is found in raw water sources, and this is a type of pathogen, a type of parasite that's very difficult to remove from water, very difficult to disinfect, better well said, because remember I stated in an earlier slide that Cryptosporidium, it takes about 10 days to disinfect. I mean, who's got 10 days when they're treating water? So there are specific challenges that we face when we're trying to eliminate some of these different types of pathogens in the water that cause us diseases. But once again, I want to emphasize that not all the diseases that we suffer coming from our distribution systems are necessarily viral and bacterial. Now, I'm hoping that this next video plays clearly because it gives a really good synopsis of the different sources of diseases caused by water in our industry. So if for some reason it doesn't play, Emily, let me know and I'm just going to skip it, okay?
For sure.
Today, we're diving into a crucial topic that affects millions of
You're
people:
good, Joe.
waterborne diseases. Clean water is essential for life, but not everyone has access to it. So, let's learn more about what waterborne diseases are, how they spread, and what we can do to prevent them. Let's get started. What is waterborne disease? A waterborne disease is an illness caused by drinking or coming into contact with water that is contaminated with harmful microorganisms or toxins. These diseases can be caused by bacteria, viruses, parasites, or chemical pollutants present in the water, leading to symptoms such as diarrhea, vomiting, and fever. What are the sources of water contamination? Human and animal waste. Improper disposal of sewage and animal waste can seep into water supplies, introducing harmful pathogens. Industrial waste. Factories and industrial plants may discharge pollutants and chemicals into water bodies, contaminating them. Agricultural runoff. Pesticides, fertilizers, and other chemicals used in farming can wash into rivers, lakes, and groundwater. Natural disasters. Events like floods can overwhelm sanitation systems and introduce contaminants into water sources. Improper waste disposal. Dumping of garbage and hazardous materials in or near water bodies can pollute them. Urban runoff. Rainwater can carry oils, heavy metals, and other pollutants from roads and urban areas into water systems. Which diseases are caused by consuming contaminated water, and what are the symptoms? Cholera, caused by the bacterium Vibrio cholerae, leading to severe diarrhea and dehydration. Dysentery, caused by bacteria like Shigella or amoebas, resulting in bloody diarrhea and abdominal pain. Typhoid fever, caused by the bacterium Salmonella typhi, leading to high fever, weakness, and abdominal pain. Hepatitis A viral infection causing liver inflammation, jaundice, and fatigue. Giardiasis, caused by the parasite Giardia lamblia, resulting in diarrhea, cramps, and nausea. Cryptosporidiosis, caused by the parasite Cryptosporidium, leading to diarrhea and stomach cramps. E. coli infection. Certain strains of Escherichia coli bacteria can cause severe gastrointestinal distress. Polio, a viral disease that can lead to paralysis, though it is now rare due to widespread vaccination efforts. How to prevent waterborne disease. Ensure clean water. Drink and use water that has been boiled, filtered, or treated with chlorine or iodine. Good sanitation. Use proper sewage systems and avoid open defecation to prevent contamination of water sources. Hand hygiene. Wash hands thoroughly with soap and clean water, especially before eating and after using the bathroom. Conclusion. Waterborne diseases are a significant public health issue, especially in developing countries. Access to clean water and improved sanitation can drastically reduce the incidence of these diseases and save lives. Remember, clean.
Okay, that's where it ends right there. But I like that the video highlighted the different sources of contamination, contaminants that could get into water that cause diseases in human beings. As you notice, it didn't all have to do with viral and bacterial diseases. Now, it's very important that, especially when we're starting off, the first thing we're going to talk about the actual viruses and the actual pathogens and bacteria that are in the water. And most of these are from sources that are called surface water sources. Now, if you look at this slide right here, you see sources of drinking water. The water that we have in our distribution systems obviously is potable. It comes from a drinking water source. Now, you see there, I count that we have 7 sources of drinking water. Really, there's 8. There's a missing source. Now it's the ocean. And there are some countries now, notably Israel, that they use reverse osmosis, these large reverse osmosis skids to treat ocean water to desalinate it for potable water consumption. But talking about the sources of drinking water, you notice here that if I include ocean in this slide, there's really 8 sources of drinking water. Of these 8, there's only 2 that when it comes to bacterial and viral infections, that there isn't really a high risk for those types of diseases being transmitted. And if I were to ask a question openly to the class, of course, now these are rhetorical questions. I don't expect you to answer them literally in the program, but I want you to get you thinking of these 8 sources that I'm talking about. Which are the 2 which are least likely to transmit pathogenic organisms to the drinking water? Now we have the stream, lake, reservoir, river, spring, pond, well, and now I just included ocean. Well, if you were going to say that the well and the spring are the answers, you're absolutely correct, because when it comes to groundwater sources, because the earth acts as a filter, they don't contain, unless they're directly influenced by a surface water source, they don't contain a lot of pathogenic organisms, because the actual earth, as the water passes through it, will filter these out. And so those two type of sources are not particularly known to transmit these type of diseases. But then you have the stream, you have the lake, you have the reservoir, the river, and the ocean, which are called surface water sources. Why? Because they come in contact with the surface. These are the type of sources that that transmit these pathogenic organisms, which cause problems to us in our drinking water. Now, these are the different types of bacteria that we find in surface water sources. Now, I think it was Allison who was talking about surface water, and she was making mention that surface water is loaded in organics, and it is loaded in organics because there's fish in it, there's birds flying over and defecating over it. If you get water from the CAP, I've seen burros, donkeys, those wild burros that live in the desert, they swim in that water, so they add that organic compact to the water, and those organics are what carry these pathogenic organisms. Now, as you can see, there's 3 categories of pathogenic organisms. They're bacteria caused, virus caused, internal parasite caused, and some of these that we see in the water we're familiar with, like over here we got typhoid fever, we got cholera, and then over here on that internal parasite, we've already touched a little bit about giardiasis, about cryptosporidium, and then you also have amoebic dysentery. These are the different waterborne pathogens transmitted mainly by surface water. And those are the ones that we have to be careful of in distribution systems. Now, how can these be taken out? Well, they can be removed or inactivated or killed by physical and chemical water treatment processes. So water treatment operators, when they correctly coagulate and flocculate and settle out the raw water or source water that they're treating for drinking water purposes, they're able to remove, and now this is very interesting right here, 90 to 95% of pathogenic organisms, if this is done right. One of the last treatment plants that I worked at, we used aluminum sulfate. Look what the comment that it says here about aluminum sulfate. It says aluminum usage can increase viral removal by up to 99%. That's prior to filtration and to disinfection. So when you have a treatment facility that is operating properly and effectively, you can remove it, from 90 to 99% of the pathogens prior to disinfecting it before it goes out into the distribution system. Filters, today we also use fine particle filters to remove a lot of these sediments in the water, this turbidity that will hold some of these pathogenic organisms. I think that Alison also made mention of what's called granular activated carbon. Granular activated carbon is like a big sponge in the water. And what it's going to do, it's going to absorb a lot of these pathogens out of the water so that we do get that 99% removal before it gets disinfected. And of course, we spent the majority of the morning talking about chlorination, about disinfecting. Chlorine is a very effective chemical that we add to water to kill or mainly inactivate pathogenic organisms. But the 4 most common type of pathogenic organisms that we find in our drinking water are as listed here. You got cholera, you got typhoid, you got hepatitis A and E, and you got dysentery. Now, if you look at the common symptoms, except for hepatitis, it's mainly gastrointestinal distress. So we ingest these pathogenic organisms, they're going to cause problems to our digestive systems. One of the main things that they cause is diarrhea. A lot of the main causes of which people who contract these diseases is that they die of dehydration, because the diarrhea is so severe that you cannot contain the water, and then you'll just die of dehydration. Now, one of the main waterborne contaminants that we worry about, especially on maybe a daily, weekly, and monthly basis, has to do with the coliform group of bacteria. Now, the coliform group of bacteria is not necessarily mean that they're necessarily bad. We have coliform in our bodies. We're not dead. We're not dying. We even have E. coli in our bodies. We have E. coli in our digestive tract. But there are certain strains of coliforms, most notably E. coli, that can do us significant harm. And where do these coliforms come from? Well, they come from warm-blooded animals. They come from ourselves. They come from, as you can see, it could be from birds. It could be from livestock. There's different sources, but it comes from animals, basically from fecal matter. And so these type of waterborne contaminants, we want to keep them out of our distribution system, because they do cause those, as you can see in the bullet point in which I'm holding my mouse here, they cause acute gastrointestinal effects, mainly diarrhea and vomiting, which cause dehydration in our bodies, and that's how we suffer from these diseases. Interestingly enough, we try to protect our distribution systems by properly treating our water in our water treatment plants, and then once it enters the distribution system, we make sure that we have at least a 0.2 chlorine residual, because when we do that, it indicates that the chlorine has gone in and has attacked all these organic particulates in the water, of which are pathogens. Part of them are pathogens, so that there's nothing left for that chlorine to react. And that's why when we take our coliform samples, if they come back not positive, then that means that our drinking water is safe. And one thing that we want to make sure that we understand about coliforms is that coliforms are an indicator organism. I'm going to repeat what I just said earlier. We have coliform bacteria in our body. The fact that it's an indicator organism indicates that there may be harmful bacteria or E. coli in the water that can do us harm. So that's why when we take a coliform sample and it comes back positive the first time, we are allowed to resample to make sure that it is not E. coli. And it is E. coli, then that's when we have a bigger problem. So how do we respond to E. coli detection? Well, the first thing we have to do is that we have to issue a boil order. Now I want you to notice what it says right here in this highlighted bold print in this slide. It says when you do get an E. coli hit, as the system is being disinfected, customers of the potable water system are ordered to vigorously boil their drinking and cooking water, and notice what it says, for 1 minute before using it. So if you do one way to protect your system, if for some reason you do get this type of contamination in it, is to boil your water. It is the quickest, most effective way to protect customers against this type of infection. Now, one thing that we want to make sure that distribution system operators, that as distribution system operators, we're in charge of all the appurtenances in the system. That sounds like a fancy word, appurtenance, but the appurtenance are the pipes, the pumps, the valves, the storage tanks, the meters, the fittings that we have in our distribution system. As distribution system operators, we're responsible for maintaining these. And when there's a water break, we're responsible for repairing these as well. So one thing that we have to make sure of is that when we do perform maintenance on any one of these appurtenances, or we do perform repair on a water break, that we're properly disinfecting our fittings, our appurtenances before putting them back in service. For instance, you have your pipes. One thing that we need to do is you're going to make sure that when a pipe is put back in place, not only is the pipe clean from the interior, but that it's properly swabbed. And you swab a pipe by running a rag with a chlorine solution through the pipe or through whatever fitting that you're installing to make sure that it's properly disinfected. Same thing applies to valves. Same thing applies to a storage tank. We take a storage tank down for service or maintenance. We want to make sure that we properly disinfect that storage tank before we put it back into operation. Just a quick question. If I was to disinfect the storage tank, at what concentration do I need to disinfect that storage tank? The answer is that it has to be disinfected with a solution of 200 milligrams per liter of chlorine solution. And the same thing, that same concept, that same general rule applies to when we're disinfecting our pipes and our pumps and our valves before putting them in service. So 200 milligrams per liter is what we need to properly disinfect those appurtenances in our drinking water distribution system. Okay, so obviously protecting the integrity of the distribution system is very important for us for keeping these pathogenic organisms out of our drinking water systems. Okay. So distribution system integrity is defined with three basic components. The first one's going to have to do with physical integrity. That means that we have to maintain a physical barrier between the distribution system interior and the external environment. That means that our distribution system pipes, our valves, whatever appurtenance, our fire hydrants, that they're completely sealed from the external environment, so it doesn't allow anything from the external environment, the dirt per se, to come in contact with the drinking water. And then this one's a very important one. This one has to do with hydraulic integrity. And what does that mean? That means that we have to maintain a desirable water flow and, most important, a water pressure in our distribution system to prevent contamination of those systems. So a good question to ask, and this is a question that comes out in our Distribution 1 treatment exams, is what is the absolute minimum pressure that you're supposed to maintain in your distribution system at all times? I'm going to repeat the question. What is the absolute minimum distribution system pressure that we are supposed to keep in our distribution system at all times? If you answered 20 pounds per square inch, that is the correct answer. We should not allow our distribution systems to drop below 20 psi at any given time, and that will assure that there will be no inflow into or back siphonage into our drinking water systems that can cause contamination from the environment. And then obviously we're talking about the water quality integrity. Are we monitoring our chlorine residuals? Are we monitoring the water quality in our distribution systems, taking those coliform samples to make sure that our water is clean and protected from any outside sources? Okay, I'm going to show this slide right here because talking about distribution system integrity, this has to do with backflow. Now, backflow is comprised of two conditions. One of the main conditions that causes bacterial and viral contaminations in drinking water systems has to do with back siphonage. Now, backflow has to do with back siphonage and back pressure, but most notably back siphonage. That's when you do not maintain that 20 psi in your distribution system at all times. And what do you do? You can cause a siphon back into your distribution system where anything that's connected to the distribution system. Now, you notice this one slide right here. This one side shows a yard hydrant, and that has a hose inside of a bucket. I don't know what the bucket may contain. Maybe it contains non-potable water, contaminated water. If I lose distribution system pressure, that means the pressure goes below 20 psi, then I create a siphon. I create a negative pressure in this pipe. So whatever this is connected to is going to suck that water back into the distribution system. You see this right here, while that hose is inside that bucket, that in the most technical terms is called a cross connection. It's a connection between a non-potable source to a potable source. And that loss of PSI is going to allow that water to go back into the distribution system. Now notice up here I have like a two-story house, and it looks like there was a vehicle that struck a hydrant out in the distribution system. Now that hydrant's going to be releasing all that water pressure out of that hydrant, causing a geyser, and the distribution system pressure is going to drop. Because that tub that somebody just took a shower in is 2 floors above the surface of the ground here, now I have a positive pressure that's going to overcome the negative pressure that exists in my distribution system, and it's going to put all that tub water back into the distribution system. So once again, I emphasize that we need to maintain that positive PSI. Now look at this next GIF that we have on here. This was an actual case in which I was working on a distribution system that lost pressure. Now, this was a controlled environment. I don't want to lead anybody to lead that we allowed anything to get into the distribution system. But look at the back siphonage that occurs. So what would happen if that yard hydrant was connected to a bucket, and that bucket maybe had, it had some type of non-potable source of water, contaminated water. You could see that when I put my hand on the spigot of that yard hydrant, it had a vacuum because the distribution system no longer had pressure. It would have sucked whatever was in that bucket back into the distribution system. And that's one of the main reasons that bacteria and viruses sometimes get into our distribution systems, because we allow the system pressure to drop below normal levels. Okay, so just to repeat a little bit of trivia, this question asks, water should be delivered within a distribution system at a minimum desired pressure of 35 psi. That's a recommended pressure. Some of us go higher. With an absolute minimum pressure, look how it's worded, minimum pressure of how much? And then you have 4 options right there. 15, 20, 25, or 30. If you answered D, you answered correctly. It is 20 psi. That is what we need to maintain in our distribution systems at all times to help prevent contamination of viruses and bacteria in our distribution systems. Now, one of our earlier presenters talked about the next contaminant that enters our distribution system. She talked about trihalomethanes. I'm not going to spend too much time on this topic since it was very, very adequately covered in an earlier presentation. But it is another waterborne contaminant that causes diseases to humans that are found, and it is found in distribution systems. Now, once again, what is the source of like trihalomethanes and disinfection byproducts in the water? It's, like it says right there, a variety of inorganic and mainly organic chemicals or compounds that react with chlorine in the water that form these different byproducts. And the health effects are not good. Trihalomethanes are known to have caused cancer. Chlorite causes neurodevelopmental toxicities. Now, this is very important for us to remember. Look at the MCLs for these different contaminants in water. This is something that's going to be asked of you in your treatment exams. For haloacetic acids, notice it's 0.06 milligrams per liter. For total trihalomethanes, it's at 0.08 milligrams per liter. Now, quick question. If I were to ask, what is the maximum contaminant level for haloacetic acids and trihalomethanes, not in milligrams per liter, but in parts per billion, what would the answer be? If you look at this next slide, you see that here's the MCL for trihalomethanes in parts per million, and you notice it's 0.08. What is it in parts per billion? It's 80 parts per billion, because there is a difference of 1,000 between both of these numbers. So don't let that fool you on your treatment exams. If they're going to be asking you these things, make sure that if they ask you in parts per million, if it has to do with haloacetic acids, that it's 0.06. If they're asking for in parts per billion, you better answer 60. Conversely, when it comes to trihalomethanes, if they're asking it for in parts per million, it's going to be 0.08. But if they're asking for it in parts per billion, it's going to be 80. And I think that Allison really clearly explained that there's different types of trihalomethanes. Trihalomethane is basically described by the abbreviation THM, but when you're talking about total trihalomethanes, it means the addition of these 4 different types to get 80 parts per million. That's what it means, total trihalomethanes. So if the addition of these 4 in our lab results exceed 80 parts per million, then we are in excess of the disinfection byproduct total trihalomethanes in water. Okay, quick question for everyone. So when chlorine comes in contact with an organic material, what carcinogenic compound may be created?
Hey, Joe,
Yes.
can we give the audience maybe a few seconds to try to put that answer in the chat box? I want to
Okay.
make sure I'm grasping this concept. If you guys can go ahead and put A, B, C, or D in the chat. Make sure you guys are understanding. So we've got a D, a few B's, quite a few B's.
Okay, if you answered B, B is the correct answer.
Oh, you guys are doing great. Thank you.
So that means trihalomethanes. Whoever answered D, that abbreviation stands for total organic carbon. Now remember that Allison in her presentation talked about total organic carbon. That's a precursor to trihalomethanes. So the reaction of chlorine with TOC creates trihalomethanes. And then it was really clearly explained that to reduce trihalomethanes in water, you basically want to make sure that you eliminate those precursors. So the treatment plant operators at the different treatment plants that feed your respective distribution systems, it is their job to do the most possible TOC removal from that source water before they put it out for drinking water purposes to their customers. The more you can take out that TOC, the less instance of trihalomethanes that you're going to have in your distribution system. Another factor that's very important too is that the longer that water ages with chlorine contacting it, the more instance or the higher instance of trihalomethanes that you're going to form. In other words, they have like a cooking time. The longer they cook, that was a term that we use in the industry. The longer that water cooks with chlorine contacting it, if it's got TOC in, the more trihalomethanes that you're going to allow to brew up. So we want to keep that water age low. I remember when I was working for EVCOR, especially in the summer, we would actually operate some of our storage tanks at half capacity because that would reduce the water age. The water did not have as much contact with the chlorine before it went to the customer's homes, and that's why it reduced the instance of trihalomethanes in the water. Okay, so once again, right here, total limit of trihalomethanes in drinking water, the MCL is 80 parts per billion, haloacetic acids is 60. Okay, this is another question that many of the guys want to answer that. I would really welcome it. What is the preferred solution to preventing trihalomethanes from forming?
Absolutely. Go ahead and put your answers in the question or the chat drop down, whatever you have access to. Let's see if these rolling in. Looks like we got a few. We've got a B, we've got an A, B, B, A.
Okay.
Looks like a balance between A and B.
Yeah, the answer is actually B. Now, if B was not an option, whoever answered A, that would have been the next best answer. You can remove trihalomethanes or the precursors of activated charcoal. Does activated charcoal remove trihalomethanes? No, they don't. No, it doesn't. But it removes the precursors to it. The precursors are the organic matter. Less organic matter in the water, the less chlorine is going to have to cook it into trihalomethanes. Okay, this is another question right here. Which of the following is typically associated with trihalomethanes? And you have A, B, C, and D options.
Let's see what we got. Looks like we got C's and B's coming in. A lot of C's and a
Okay,
few B's.
and a lot of C's is the answer. Water with organics that has been chlorinated. Remember, chlorine, the halogen chlorine, when it reacts with organic, that's when what's going to give you the trihalomethanes. Now, I'm going to repeat something that Allison said. I know that she had a really tough job because she had to cover a lot of material, but when she was talking about organics, she says, hey, don't think about the organic section at Fry's where you have all that healthy food that hasn't been hit with pesticides. Organics, when it comes to water and chemistry too, means a totally different thing. So my question to everybody in attendance, how would you, in water treatment terms, define an organic compound or an organic material? How would you define it? If they can give you an answer, that I would appreciate it.
Definitely. We got carbon-based, something with carbon. Looks like they grasped that. Yeah. Anything that wants to live. Thank you, Ryan.
Okay. If they answered anything with the element carbon, they are correct. In chemical terms, an organic compound is anything that contains the element carbon. So are we organic? Yes, we are, because we contain carbon. Remember, carbon reacts with a halogen chlorine to form disinfection byproducts, most notably trihalomethanes in our distribution systems. Okay, let's go into another contaminant which causes disease in our distribution systems, and this time we're talking about nitrates. Do you remember that video that we saw initially? And it showed a tractor and it was spraying, it was either spraying pesticide or was spraying fertilizer over a field. And notice what it says right here about the sources of nitrogen. It's naturally occurring. It occurs in vegetables, but it's contained in sewage, animal waste, and fertilizers. Now you notice that whoever works wells here in the state of Arizona, I made mention that well is a groundwater source and it's not affected by the surface. So how come our wells sometimes are loaded with nitrate? There's one well that I monitor for a treatment process that I am responsible for that has nitrate levels about 14 to 18. They tend to vary. I'm like, where the heck did this nitrate get in the water? Well, it came in the form of a fertilizer. So I ask everyone here, what is the purest form of nitrogen that we add to our crops that creates nitrate in the water?
Looks like we have someone you listed fertilizer.
Yeah, well, yeah, fertilizer. Well, what type of fertilizer?
I see. Ammonium nitrate, compost, more ammonia.
Okay. And I do appreciate the answer, and I appreciate that everybody's attentive. The answer is ammonia. Now you look, this is a chemical symbol for ammonia. So you see it's an N. This is nitrogen with 3 hydrogen molecules attached to it. Ammonia is the purest form of nitrogen found in our water, but we don't necessarily see it in the form of ammonia. We see it in the form of nitrate. I'm not going to get into a real detailed explanation of how this occurs, but there's bacteria in the ground, naturally occurring bacteria, that will convert that ammonia into nitrite. Now, once they convert it into nitrite, they convert it into this compound, which is called nitrate. Nitrate. And what is the limit of nitrates in drinking water? If you look right here, the maximum contaminant level of nitrates in drinking water is 10 milligrams per liter or 10 parts per billion. Why is it that we don't want nitrogen in our drinking water? That's a question for everybody. I would really appreciate if somebody gave me an answer to it. Ebony.
Yes, let's see what we got coming in. Baby blue syndrome. Yep, blue babies, yeah.
And that is correct. Blue baby syndrome is an easier term to describe this word right here, this monosyllabic word. This is methemoglobinemia. And that's called blue baby syndrome. You see that image right here? That's an infant. That infant normally does not have blue eyes. It's probably a brown-eyed infant, but now his eyes are blue. In a more extreme place, you see this individual right here in the bottom right, left corner and the right corner. He's suffering from methemoglobinemia, blue baby syndrome. Now, how is it that nitrate in the water causes us to turn blue? Now, if I were to ask everybody, when someone is deprived of oxygen, when someone is drowning or has drowned and has been revived, they say that one of the first symptoms that shows that they have drowned is that person's lips are blue or their skin is starting to turn blue. And what does that mean? That person is not absorbing oxygen. And that's what nitrate does to us, to our bodies. Infants are the most susceptible to the effects of nitrate in drinking water. Because nitrate, when it gets into our bloodstream, what it does, it prevents us from absorbing oxygen. So you can be breathing, a child can be breathing, but still suffocating if he's loaded with nitrate because his bloodstream cannot transmit that oxygen to his body, to his tissues, because of the high nitrate contact in it. Now I want you to look at this slide right here. Those are kosher hot dogs. Now kosher means that no preservatives have been added. Now you see this right here? You see this where my mouse is? It says no nitrates or nitrites added. So based on what we already know, why do you think the FDA allows for a certain quantity of nitrates and nitrites to be added to our cheeses, to our sausages, our hot dogs, our bacon? Why do they do that? They do it because it's a preservative. Because see, these pathogens, these bacteria that decompose our food, they also need oxygen to survive. You put nitrate or nitrite in our food, that bacteria cannot survive and decompose that food. They cannot rot that food. But at the same time, we eat that nitrate and that nitrite, and we're the ones that are suffering the consequences. And that's why there's a big push now for the FDA to prohibit the addition of nitrates or nitrites in our food. But unfortunately, it's in our drinking water, and that has to be taken out. And one of the main ways that we take it out is through reverse osmosis treatment systems, or we dilute it out. I think Allison talked about how you can actually dilute water with low nitrate water to reduce the amount of nitrate in water. So quick question for everyone. What is the limit of nitrate that we should have in our drinking water?
And if I'm correct, you did just say it. There should be no wrong answers. 10.
It is 10. Okay, quick question for everyone. Ebony, what health risk is associated with nitrate in water?
Go ahead and put in your answer, A, B, C, or D there. Got a lot of B's. We have one C so far, one A. Looks like we're divided between the first three.
It's actually blue baby syndrome, methemoglobinemia. Remember, nitrate does not allow us to absorb oxygen, so it makes us very sick. Okay.
Joe, on that question, can you just clarify, will this blue baby syndrome, does it take the oxygen out of the blood or just impacts our absorption of oxygen?
No, it doesn't take it out of the blood. You're still breathing. It just doesn't allow your body to absorb it. That's all it does. Okay, as time is pushing us, let's go into the next contaminant, which has to do with arsenic. Anybody also who deals with wells here in the state of Arizona, they deal with arsenic levels in their wells. Okay, before I go into the next slide, since I have a bunch of experienced operators in my audience, what is the limit of arsenic in drinking water?
Got 5 seconds. We got 10, 10, 10.
Okay, 10 what?
We've got parts per billion. We've got parts per million.
Correct. It's 10 parts per billion.
Yep.
How does arsenic get into our water? One of the main sources of arsenic in our water is through pesticides. The pesticide DDT contained a lot of arsenic. DDT has been banned now for use, but one of the main components of DDT, which was toxic to any of these pests that were getting into our crops, is arsenic. Another thing was malathion. Malathion used to be extensively used also for pest control. And so that is also contains a lot of arsenic. So that when they were spraying that over the fields, when those fields got irrigated, that arsenic infiltrated into our groundwater supply. And now we have to deal with it. And what are the health effects of arsenic? It causes skin damage, but most notably, it causes cancer. And it could cause cancer in our lungs, our liver, our pancreas, and our stomach. So it's very important that we keep that arsenic out of our drinking water. Now, as you see, the MCL is 0.01 parts per million. If they ask it in parts per billion, it's going to be 10 parts per billion. Okay, so this slide details some of the effects of the arsenic in our drinking water. Look what arsenic poisoning does: skin damage, increased cancer risk to different organs in our bodies. And I thought this slide was very interesting. So this is a slide of the United States. The darker the color you get, the higher the instance of arsenic in your drinking water. Look what the state of Arizona, where we live in, look at the levels is right there. We have very high level of arsenic in our drinking water. All this California, Washington, Texas, agricultural areas that used a lot of pesticides to control pests damaging crops, they now suffer the consequences of arsenic in drinking water. We got to keep that below 10 parts per billion. Okay, Ebony, time is kind of pushing us, so I'm going to get into lead and copper. Most notably lead. How does lead get into our drinking water? That's a very good question. But lead causes neurodevelopmental problems in children. Copper will cause liver and kidney damage. Sometimes a little bit of copper in the water is not bad. It's actually good for us. It's a mineral that our bodies need, but too much of it also damages. Okay, quick question for everyone. What is the chemical symbol for lead on the periodic table of elements? What is the chemical symbol for lead?
BB.
That is correct. And what does that stand for? That's Latin for what?
Bonus point. Plum board. Plumbus and plum.
No, it's, well, very close. It's plum bum. Plum bum. Plum bum is a Latin word for lead. Back in the day, in the early turn of the century, all our water pipes in our homes and our distribution systems, they were made of lead. It was cheap, it was light, it was malleable. And that's why those workers that used to work on pipes in our houses that were made of lead, they called them plumbers. That's why the term sticks today, plumbers. It comes from the term plum bum, because our pipes used to be made of lead. Nowadays, we no longer make our drinking water pipes out of lead, because as we can see, lead causes problems in our bodies. Look at this slide once again. Look at the effects of lead poisoning. High levels of lead causes mental retardation, coma, convulsions, and death. And even just low levels of lead causes IQ issues, reduced IQ, impaired growth, reading, and learning disabilities. And why is that? Because lead, once it gets into our brain, you can never take it out. We haven't figured out a way to detoxify our brains of lead if it happens to get in there. So we need to keep it out of our water. So in our homes, what are the sources of lead in our water? Sometimes copper pipe has a lead solder, especially if you build a house before 1986. The solder that we use to join our copper pipes, it contains lead. If you had a lead service line, so if your house was built before the 1950s, most of the service lines were lead. So that lead can get into your drinking water, and certain fixtures in our faucets in our homes contain lead. And this is an interesting thing. Galvanized pipe, which is still in use today, and it's sold everywhere. You go to the Home Depot, you go to the Lowe's, you can still buy galvanized pipe. It does have lead in it. Not extremely elevated levels of lead, but it does have lead in it, and that lead can also leach into our water systems. What causes the lead to leach out of pipes? What causes it is corrosive water. Now, if you see this right here, these first two, this is lead pipe and this is copper pipe. I'm going to focus on the first two, which is a lead. This is lead treated and this is lead untreated. Now, if you see the difference between the two, this one in the middle is starting to corrode. What's making it corrode? It's low pH water, corrosive water. Now, what am I getting at? Look at this lead that's treated. If you were to really examine it, I hope the picture is not too grainy, but you notice that this lead pipe has like a little coating in it. You see that? That's like a little bit of scale that it's forming in there. Believe it or not, scale in drinking water pipes is actually a favorable thing if you can control it. Now, I'll give you an example. This is a pH scale right here. And on the one extreme of the pH scale, I have a chemical called sulfuric acid. On the other extreme, I have a chemical called this right here, this NaOH, that's called sodium hydroxide. That means caustic soda. Now, one of the last treatment plants that I worked at, we used both of these chemicals, really nasty, dangerous chemicals to work with, but you need to have them in your drinking water systems. And I'll go on to explain why. Because see, here we are, we're taking the raw water coming out of our CAP canal into our plant. That raw water has very high alkalinity in it. Now, if I were to ask everybody here, what is alkalinity? Alkalinity is basically like having baking soda in water. When my car battery leaks acid, you know what I neutralize that acid with? I use baking soda. Once I put baking soda on that acid, I could touch that acid and it's not gonna burn me, because baking soda or alkalinity will neutralize acids. If you're trying to properly coagulate and flocculate water to be able to get those particulates, that turbidity out of the water, it cannot have a lot of alkalinity. Why? Because that water needs to be a little bit more on the acidic side of the scale to be able to coagulate and flocculate it. I'm pretty sure there are some operators here that worked at treatment plants. When you have high alkalinity water and you're trying to coagulate and flocculate that water, you're adding aluminum sulfate, nothing is happening. The water is still very turbid. You don't see that flock forming. You're thinking, what the heck is happening? That's called dead water. It will not react. How do you get it to react? You destroy the alkalinity. How you destroy the alkalinity? You add this chemical right here called sulfuric acid. Sulfuric acid is so powerful that when you start adding into the water, it destroys the alkalinity in the water, dropping the pH. So this water coming into my plant was normally at a pH of 8 to 8.5. We add the sulfuric acid, dropped it to about 6. Now magically I start getting this wonderful coagulation and flocculation. This big beautiful flock that's settling out of my sedimentation basin. Now my water looks really clear. Now I'm happy. My filters are operating at an optimal level because they're not plugging up because there's no particulates going in it. But then here's the problem. Now my water going into my storage tank prior to going into the distribution system has a pH not of 8.5, but a pH of 6. That 6 pH is going to be corrosive to the pipes in my distribution system. It's going to be corrosive to the ductile iron pipe. It's going to be corrosive to the galvanized pipe and copper pipe in my house. So I cannot allow that 6 pH to go back into my distribution system. Then I have to add a chemical at the end called sodium hydroxide, which what does it do? It alters the pH and it adds alkalinity once again to the water. And once I start doing that, I start forming that scale. Now this is a little bit extreme, but I had to incorporate this picture because that scale formation in your pipe is what protects your pipe from lead and copper and iron or any other metal from leaching out and getting into your distribution system. So distribution system operators have to work really closely with the water treatment plant operators to make sure that the chemistry of the water is such that the pipe is not corroding. Because if it's corroding, then the addition of certain treatment chemicals to form that healthy protective scale will help keep that lead and that copper and that iron from leaching into your distribution system piping. And of course, you can play with that chemistry. So when you see that scale getting a little too thick, then we're going to control the pH so that the pH starts dissolving that scale. And then once that scale starts dissolving and we see that it's getting too thin, then we change the chemistry again to help that scale to start build up again. Okay, time is pushing us. A quick question for everybody in the group. Ebony, what is the chemical symbol of lead?
Final answer, PB. B.
Maybe. We know that stands for plumb bum. Okay, what is the MCL for lead in drinking water?
Jim got it, 15.
Yeah, it is 15 milligrams per liter, 0.15 milligrams per liter, or 15 parts per billion. Now, mind you, this is what's called an action level. Okay, you see right here where it says AL. It's not an MCL, it's an AL. It's an action level. That means that, hey, you better do something about that right away to keep that level of lead down so it doesn't get too high. And the action level for copper is going to be 1.3. Now, I just wanted to show this last slide for everybody in the group. It says, how do you reduce lead exposure in water and clean out your faucet aerators? This one is very important right here. It says, run cold water 3 to 5 minutes before using it if it has not been used for several hours. So you get up very early in the morning. You know, we distribution system operators, we get up at 5 to show up to work at 6. And then we go to the kitchen faucet. And the first thing we do is we put our drinking water cup under the faucet, and then we pour that cold water into our cup. Don't do that, please. Because if that water has been sitting in that pipe, if that water is a little on the corrosive side, it's going to be leaching out metals into the water. And if you have any type of lead in your plumbing, you're going to be drinking that lead. So let it run for a couple minutes before you actually start using it for drinking water purposes. Okay, Levany, I'm sorry that I went over time. That's the end of my review.
Well, thank you very much, Joe. We are at time and we will go ahead and end this webinar. Hector, we did see your question. We'll go ahead and direct that to Joe. We just want to give a special thank you for all of our presenters, Joe from Aqua Prairie Utilities, Allison Shepard from City of Phoenix, Frederick Tack from Consor, and Karen Shannon, our own in-house unit manager for the drinking water inspections, compliance, enforcement. Please make sure you grab a handout, an agenda through the handout section. I just learned if you're on an iPhone or you use Safari, the option isn't handout, but materials, that you can pull that drop down and you should be able to grab the agenda. Plenty of thank yous from the audience to our presenters. We hope this webinar was value added, not just showing the importance of chlorination disinfection at the treatment plant, but also beyond, whether the distribution or the hauling process. Once again, please make sure you get your PDHs, and if you have any issues, please contact the OpCert program. Our email and our phone is listed right there on the final slide. Dean, if you need an agenda and you can't see it in the handout section, go ahead and IM me. I'll send that your way. And we'll close this webinar in about a minute. Once again, this webinar was recorded, and we will have this up on our YouTube page within the next few weeks. That's okay, Hector. Please email us if you cannot get the agenda or you do not see the handout or materials option. We will send you an agenda. That's okay, Dean. This webinar will be recorded for future viewing too. All right, once again, thank you very much for your time and your participation today. And everyone have a good afternoon and a great weekend.